and welcome to this tutorial. I'm going to be doing the ray tracing in one weekend series. I'm going to be starting with book number 1, and that's probably what's going to be for this video. And I'm going to be doing it in the Zig programming language, which you can find at ziglang.org. Zig is a new systems type language, and basically it has a lot of powerful features, and hopefully this is a nice walkthrough through a relatively advanced project using Zig. If you want to get started with Zig, you can go ahead and go to the download section where you can pick up the latest binaries either from master or 0.11. I believe I have installed 0.11, which is the last stable version. A lot of people will recommend you, however, to use the master build if you're going to be building anything and want to basically be always up to date. These builds are always being refreshed, and they're newer than what you'll probably find in most package managers. Another good way to find Zig documentation is to go to the documentation screen here, along with this Zig standard library documentation, which has a lot of useful things from the actual standard library itself. Without further ado, let's go ahead and get started with ray tracing in one weekend. And what I'm going to do is I'm going to create a directory. So rt1 weekend, cd that, and then Zig init-exe will create the first Zig binary. I'm using Astro and Vim here, pretty unconfigured. The only thing I've done is done lsp install zls and the command ts install Zig. And lsp install installs the Zig language server, and ts install installs the tree sitter plugin for let me try and get that. We'll get that out of the way. This is the build.zig file. Zig uses a build system. Essentially, the build.zig file contains all the instructions, and it's a completely declarative format. So even though this looks like it is imperative, everything is actually being constructed into an object. So there are steps that are depended on, and that's how everything gets set up. You're basically just filling out data structures, and eventually those get used. There's quite a bit of default commenting here, and the other thing we'll look at is the main.zig file. In main.zig, you just have the standard debug print. This is good for most purposes. Technically, if you want to use a standard output, you use this get standard out writer method to write much quicker. You want to use a buffered writer. It's just better in most cases because default writing is going to be a system call for each time, and you want to preserve the number of system calls you want to do. There's also this testing framework. Zig has an inbuilt testing framework, and basically you start with test and a name for the test, and then you can write out a test here, and you use this standard testing expect equal. If it fails, it's going to trigger an error, and you'll see that your test fails. Otherwise, you're going to get something that works. So if I change this to 41, and then I create a new tab, that number is completely random, but okay. Then do Zig build test. It will run the tests. And the test will fail, so you'll see test 0, 1 passed, expected 42, but you got 41. If I save it and then rerun the test, you see it passes and doesn't say anything. So then Zig build run will show the actual content of this file here. And I'm wondering why my hostname is screwed up. Either way, I'm going to delete like 90% of the content in this file here, because we're going to be starting to follow along with the ray tracing in one weekend book. Alright, so let's get started. So there's the general overview, which you should probably read. First thing we're actually interested in is creating a ppm. So ppm is a file format, and essentially it's got what you're going to render your image to. It's extremely easy to understand. So to output such a thing, a C++ example here for creating an image. And it creates this output image. So we're going to go ahead and try to do this. We probably want to declare it in a structure, so we'll have a const ppm, which is equal to a struct. So the struct for ppm will take in a width and a height, and it will need some degree of data. So let's get started here. We're going to create a function called init, which is going to return the ppm itself. If there's an error, it should return an error. I don't think there's a way to really make an error happen here, but maybe there is. So we'll keep that there. It'll have two fields, which will be width, which will be usize, and height, which will also be a usize. Usize means that it's an unsigned size type, and size type depends upon architecture. Usually, I believe it is the pointer width. So on a 64-bit system, usize is 64, and on a 32-bit, it should be U32. And we'll probably want to have the actual, probably want to get passed in an actual piece of memory and output it to a file. So I think for a ppm, we should have it be a file output. It can be both storing the data itself and being the file to output. So to do this, we're going to have it have a section of memory, which is going to be the data itself, which is going to be a slice, not an array, a slice of constant, not constant, it has to be modifiable U8s. And that will probably represent the results. All right, so then we're going to do, we're also going to take in an allocator here. So in Zig, you pass around the allocator so you can specify how memory is being managed. So we'll do standard memory allocator as what we pass in, and we'll also pass in the width usize and the height usize. And inside of here, we're going to do, first off, we're going to create an instance. So we'll create an instance of self called ppm, and to have something be just completely stack allocated and uninitialized, it's undefined. This is equal to alloca in, I believe alloca in LLVM-IR is the exact instruction. And we'll be returning self because that will be the output. So self dot width is equal to width. We could actually specify it here by doing self equals ppm, and the ppm will have the dot width equals width and dot height equals height. And then for the data, let's actually make this so that it looks like this. We'll do dot data equals try allocator dot alloc, and as you can see with the alloc here, allocates a array of n items of type t. So what we're going to do is we're going to pass in the fact that it's U8s, and we're going to pass in the amount, which is width times height. If I save that, it should work. We'll also have a function for deinitialization, which will take in self now, which is a pointer to a ppm. And when you have something declared with a pointer to the member of what it is, you can actually use it as something like ppm.deinit, and you don't have to actually specify the argument. And this will be a void. In Zig, it's a convention that you should have something that gets initialized. Initialization may have errors. Something that deinitializes does not have errors. It's not supposed to be able to error. And we'll also need to pass in the allocator that we used Or we could actually in here store a reference to the allocator that we want to using. So we could store a field allocator, standard mem allocator, and then we'll say dot allocator equals allocator. And that would be fine as well. And then we would just do self allocator free self dot data. And then to render this output to the screen, or actually to a file, we would have a method called pub function save to file. There are various naming conventions. Choose what you want. The standard library has a set of naming conventions, and it's kind of mixed and matched. I don't know if there's an official style guide yet, so this will return error type or void. So to save to the file, we'll need first the ppm actually, and then the next thing we'll do is we'll need a file name. So the file name is going to be a slice of constant U8s. And what we can do is we do var file equals standard IO. Sorry, is it standard file system? I was right. You get the current working directory, and then you're going to open a file from it, and the file name is going to go to here. And I believe there is a flag section, and I'm not going to set any flags. What I'm going to do is defer file.close. I'm going to check really quickly, and in here we can do standard file system, etc. Standard file system, or we can actually go find open file, and we can find file system directory open file. Takes in a directory, a path, and then the file opening flags. The opening flags will have a lock mode, and then an open mode. So we're going to set the mode here, dot mode equals to whatever this open mode has, which is read only, write only, or read and write. We're going to do write only. And then let's look at how everything is being converted here. So I is being converted into but this is for the purpose of creating this output of 0, 1, 2, 3, blah, blah, blah. When we already have everything rendered out as pixels, we just need to output the pixel values. So what we could do, and they are in text, if I believe. Yes, they are in text. So what we could do is that we can get a writer to the file. So what we would do is 256, 255. So what we'll do is we'll get a writer. So var f writer is equal to file.writer. And what we'll do with f writer is that we need to implement this header. So what we'll do, file writer should have so this will just be a writer interface. So standard IO writer has usually a print. And what we could do is we could do print, and then this would be possibly erroring. Alongside of this one, this one could contain an error, so we'll do try here, and that will kick it up to the next scope if it fails. And we could have an error defer. So what we could do is, to be very safe here, actually there's nothing else. Yeah, what we could do to be very safe is that if there's ever an error, we also just close the file. So error defer file.close. In the case of an error, we just want to close the file, and that'll be it. Technically, you can do like assignments in a defer statement, but I believe you cannot raise errors inside of a defer statement because that wouldn't make sense. So then we'll do try fwriter.print, and what we're going to do is we're going to print, I believe they said it's P3, starts with P3, and then it starts with the width followed by the height. So P3 \n. Then we'll do a format string based by another format string. And then the next one will be the max values, which is 255, and then we'll get a new line. So inside of our format string, we're going to create this is an anonymous tuple, and what we're going to do is we do self.width by self.height. And now that we have that, we have the initial formatting set. So what we can next do is we can do you can either do a for loop or a while loop. Here I'll do a for loop. So you can do for self dot data in the entire range. So 0. You actually can do self dot data and not set a range here. But then we'll do a 0 dot dot here. And what this is that you have multiple captures inside of a for loop. The first value here is going to be the actual data. So this is the pixel. The next one is going to be the index. So now I have two captures, which is the pixel and the index. The pixel comes from self.data, and the index comes from here. If you want to be able to write into self.data, you would do a pointer here, so that the pixel is a pointer. And then you could write to the value of whatever the pointer was. So what we're going to do is that it seems we need to do red, green, and then blue. And right, we haven't formatted our data yet. Our data is in a U8, but actually it's going to be 3 individual components for red, green, and blue. What we can do is actually we can define a constant to say that our RGB value is equal to a union between a pixel value, so value, which is U24, or we could do a this should be called the color, and we should define constant RGB, the structure of, and it has to be packed, so there's no padding, of R, which is a U8, G, which is a U8, and B, which is a U8. So now we have RGB, and then we can do RGB, which is just the RGB structure. And what we can do is then we'll have data is color. So now we have an array of something that is always of size U24. I don't believe it's a packed union. Let me check that really quick though. It is a packed union. My bad. Is a packed union that will be of size U24. So there will be no padding added. So then we will allocate a color times that many, and then we now have a way to write to it because each pixel is a color. So it has an RGB or a value tag. So now we can get out our RGBA values, and we can use that inside of this method here. So what we're going to do is we'll do try fwriter file writer dot print, and then it's going to be this space this with a new line character. And what we're going to do is we'll do pixel dot RGB dot R, pixel RGB G, and pixel RGB B. So now we'll have red, green, and blue. And we didn't need the index. I was thinking about doing a file indexing operation. We actually don't need to do that. We just have the data itself. Yeah, so now we have a way of doing that. We have a way of save to file. So next thing that we got to do is we got to do this generation method. So what they're doing is they're doing a bunch of conversions. Let's get that sorted out. So to start with, they set up an image height, so constant image width. The U size is equal to 56. Constant image height, U size is 256. And then we're going to do a two-sided for loop. So what we're going to do is we're going to create an allocator first because we want to allocate data so that we can actually have a ppm as a class. So what we're going to do is we'll have constant, or we'll have a variable GPA, which is going to be our general purpose allocator, which is standard heap general purpose allocator. Takes in this, then we'll do dot init. And then this is general purpose allocator returns like a type of itself with a specific configuration set up, and you can change what the configuration is. In this case, we just want to perform init on that. So then we can do a constant allocator equal GPA.allocator. Then now we can create our ppm, which will be a ppm.init. This is actually try ppm.init. And we're going to give it the allocator. And we're going to then give it the width and the height. So we'll do image width and image height. So now we've created a ppm. We're going to defer ppm.dinit. And then we're also going to go ahead and start loading the data inside of it. So we're going to do a variable I, which has an integer type. So let's do, I think everything is fine if we just did a U32. So we'll do while I is less than the image width. And then you can do this colon and then put a statement inside of here. And this will execute at the end of every while loop. So we can do I plus equals 1 to increment our loop. Note that Zig does not have an plus plus operator, so you have to use plus equals, which avoids a lot of confusion in many cases because you don't know when plus plus actually gets executed, especially when you have like prepend plus plus versus post or prefix versus postfix. Sorry, you won't necessarily know how that orders. So let's see, I plus equals 1. Okay. So then we'll set auto. So we'll do our var r equals this over image width. So in order to cast something in Zig, some casts are easy to do. So if I wanted to do r as a u size equals I could, because this is an upwards type cast. So u size in this case may or may not, but is usually larger than u32. So then u size equals I. This is an upward cast. If I was explicit about it and did u64, you could do this as well. You can do explicit upwards cast, but if R was u16 and I set it equal to I, this will give you an error because you're doing a downcast, which is undefined behavior. You have to use @truncate with integer types or @trunc with floating point types. Truncate will basically reduce down the number of bits, and it will do the same like behavior that you think that it should do in C, but this is the way you have to do it because it's not necessarily defined how you want to do it. So in this case, we're actually converting to a double, so we're going to be doing @as. Actually, I think we can do @int or float from int. And sometimes the LSP decides to delete that, which is fine. So you can do float from int for I, and that should work as well. Float from int must have something. Have a known result type. Right. Oh, I need to give it a type. So this is a double, which is actually an F64, so we could do that. And then you do G is an F64, which is float from int as well. J. And var B, which is a float 64, which is 0. So to be honest, we don't really need to change it, but we'll do it for now. 0. And then what we can do, right, this uses J. I didn't do the second part of the loop. Var J, U32 is 0, while J is less than image height. Or, sorry, I think I flipped that. var I is the internal, var j is the external. This is j, this is j, this is j plus equals 1, this is image height. Var j u32, while I is less than image width, I plus equals 1. And then define this as I. Formatter did not quite catch it correctly. So I want these to be indented. And the discards there, the discards, everything must be used. Otherwise, this will give you compile error. The formatter will just get rid of unused statements for you. Or variables that are defined and not explicitly discarded will have that issue. So then, now that I have a float from the integer, I can then do the division of yet another float from integer. Float from int. Which will be the image width minus 1. Same thing will happen here at float from int image height minus 1. And now it's become ambiguous what this is, so let's do as f64, as f64. So when the system cannot give you the exact information, you just have to make sure that you explicitly specify it using as. These are compiler like built-ins. It's made to make sure that you know what you're doing in a block of code, because it's very obvious that there's something weird going on whenever you have an @ symbol and then like a bunch of code like that. It's kind of nice in a way. So then we need to do r times equals 256 and g times equals 256, or 255.99 is what they say. Sure, we can do that. And b times equals 255.999, even though that's like a constant value. Now we'll say pointless discard, so if you save it, it will fix that. And there we go, it gets out of my error log now. Then we can go ahead and write the actual data into the ppm. So ppm.data at, so I is the image width plus j times the image width. Then this actually needs to become at, you'll need to make this a usize as well, because usize is the only correct way to get into int cast in order to index into and then this is equal to an RGB structure. Okay, let's go. Let's do this in a different way. Let's calculate the index as a usize, which is I plus j times image width or height, image width. Now that I have the index, now I can get the byte versions of RGB and A. So what I can do is br equals at int from float r, and make sure br is set to u8. G is u8, that int from float g, and bar bb u8 equals that int from float b. And then so we have brgb, and then we have an index, so we could do ppm.data at index equals rgb, where .r is r, .g is or .r is br, .g is bg, and .b is DEV. Save that, and then once we're done with that while loop, we can descend one more and do ppm or try ppm dot save to file, and we'll do test.ppm. Now that we have that done, we can do zig build, and I'll probably get an issue. There's no member named in. Let me check the general purpose allocator. Center heap general purpose allocator. Uptime takes into config. That is correct. Oh, my bad. It's not an init. You just actually do an instantiation like that. My bad. Then expected main.color found main.rgb. So we need to do color as a component.rgb equals RGB, and then do that, then have that. So we could actually go and do it like this, and we say RGB and do it like that, or Zig formatter decides that that's the right way of doing it. So we'll do that, and then we'll do zig build run, and we did get an error. Where there's a file not found error. Oh, it's because I did open file. I meant to do create file. That's my issue. Where is it? Open file. No. So we want to do actually create file. And when you do create file, it's different. Directory, create a file, create flags. Yes. So we can do that. And that should give you default default write access. And then we can now look at the test.ppm. I think I just have to browse to it. Yep, and the test.ppm looks exactly like the one that we find here in the tutorial. Now there is this progress indicator, which you can add to say how many scan lines are remaining. This could be okay. If we're going to do this if we're going to call this our render method, then yeah, it's probably a fine thing to do. You would just calculate that either as number of scan lines remaining or as actual, either number of scan lines are remaining, or you could do it as a percentage. That's what I was trying to say. Sorry, I blanked there. Let's go. So now we can go ahead and add a percentage remaining thing here. So we could say they're using clog. Zig has a similar thing. It's called just standard log. So what we can do is inside of this, we do standard log info, and we could say scan lines remaining, and backslash r just goes back to the beginning of the line. That's carriage return. So scan lines remaining, and then you could do this, and then you would say the number is equal to image height minus j. And then you could even do a percentage here, which would be the image height minus j as a float divided by the image as a float. But it's quite fine for our purposes here. And what we could then do, actually, you probably won't want this to be a debug print. And the reason being is because standard log will actually insert a new line at the end, whereas standard debug print does not. So that's probably correct. And also, it doesn't clutter your SCD out. So that's probably the better choice. There, debug, print, done. And it always takes a tuple. So if you have nothing, no format strings like this, then it will never read into that tuple. So you can just set the tuple to be blank. So standard, we might want to do, yeah, we'll make it the same as the tutorial. Interesting. That did not count down the way I expected it to do. I think the reason might be that it should flush. So I am a little bit confused. So \r in my terminal does not seem to actually clear the line. Either way, it's probably fine to do \n, and we'll just remove that. Unfortunately, it doesn't work in my terminal, so there's no point. There might not be a very good reason to do this. There might be a way to mess with the scan lines, but it's probably fine to just do this. Yeah, it's okay for now. It will clutter your terminal, and I'll see if there's actually a better method of doing this. But that's actually it for for setting up it and getting chapter 2 to work, and we'll get on next with the Vec3 class and chapter 3. Hello and welcome back to this series of tutorials in Zig. We're going to be doing chapter 3 of ray tracing in one weekend. In the previous installation, we pretty much did the basic setup and we did the basic PPM code to get something out as an image. Now, one thing I did notice with our PPM image generation is that it is a bit slow, and actually the reason for that is because when you do a print under the hood, there is a write command, and the write command itself ends up becoming a Unix system call, and kernel system calls can take a pretty long time. So we actually want to store everything and do one big write all at once because it's way faster than doing multiple small writes over a period of time for each pixel. So what we can do is we can do var bwriter is equal to standard.io.bufferedWriter, and we can just wrap in the file writer here. And what we can do is we replace fwriter with bwriter. Now that bwriter is completely done with everything, we can do bwriter.flush. And that guarantees that all of the data inside of the buffered writer ends up getting written into the file writer. So now if we go ahead and zig build run, let's see. bwriter does not expose the interface real quick. So what we could do is you can make the buffered writer like that, and bwriter is the writer of the buffered writer. Yeah, that's not very clear, but buffered writer itself is like can contain the actual writer method that we want. Whoops, sorry, buffered writer. Writer. And then now we don't want to do bwriter.flush, we want to do the actual buffered writer flush. And oh yeah, that can error, so we need to make sure that it's wrapped in try. And that is a lot faster than what it was before. It's pretty much instantaneous. And that's because every line beforehand, when it was getting printed out here, was pretty much being its own system call. So in a 256 by 256 image, you can start to really stack up some system calls. So 6065K system calls is the total amount. So yeah, you don't want to do that. So it was a bit naive, and it was a small oversight that I noticed. So the next part we're going to be doing is the vector 3. Zig itself has like a thing called vector. Let me find it. But in Zig, a vector is actually going to be it's actually a SIMD construction rather than being a construction on anything else. But it could be a useful way of representing and speeding up our program actually. So it is worth trying to get done. Now, vector is a group of booleans, integers, float pointers, which are operated on in parallel using SIMD instructions. Vector types are created using the built-in function vector. Vectors support the same built-in operators as their underlying base types. These are performed element-wise and will return a vector of the same length as the input vectors. It is prohibited to use a math operator on a mixture of scalars and vectors. Zig provides the @splat built-in to go from a scalar to a vector, and @reduce to convert vectors to scalars. Vectors also support assignment to and from fixed length arrays with comp time known length. So theoretically, we can do everything we want to using vector types, and we're going to try that. We're going to test out how well this works. So there we go. Excessively long vector lengths can cause compiler crashes. We're not going to be doing anything too absurd, so we should be fine. So the vector3 class, vector3 is just a three-dimensional vector, and in many systems, vectors are 4Ds, uses RGBA, or for example, 3-position plus coordinates for geometry. It's very common to see vector 4s actually used, and that's probably one of the things to do. But we're going to implement a vector3 class. So we're calling it vec3, and this is kind of the GLSL style of naming here. So const vec3. I kind of want to capitalize the first one. It's a structure. And if you haven't kind of caught on, structures in Zig are kind of classes. I don't want to say that because you can't inherit it, but they are the method of unit organization. In fact, everything is a struct, including a file. A file is a struct as well. So if I were to put in a file directly, the contents of ppm, then import the ppm as a file, it would actually work as a structure. You could do that binding. So that's just to say that everything is a structure. So first off, we're going to have the actual elements of the array. So they call it E. I'm going to call it data. That's just me. But what we're going to do is we're going to do data, and it's going to be 3 float 64s. And I don't believe we have to set it, but we probably should set it to be all zeros. 0, 0, 0, 0, and 0, 0. And it should be equal. Oh, we were doing that form. Let me check. Right. Actually, let's ignore that for now. It's probably fine if we do an initialization. So we'll have a function called init. I mean, we don't really need to have a function called init, but we'll do it anyways. That returns you back a vec3, and it can't really fail, so it's going to return you back vector3. So we can do x, easy to think as x, y, z. So I'm going to do it that way, x, y, and z. And there should be a way to convert between that and set individual elements. It does look like it is element based, so you could do D0, or sorry, we'll create a vector, so we'll call it self. the variable self vector 3 if the data equals to 0, 0, 0, 0, and 0, 0. Sorry, not that, but this. Expected something. Expected that after statement. There a reason. We could do equals add vector for F64. And then do that. Yeah, there we go. That works. And it will format it for me. Thank you. Self. It's not 4, by the way. It should be 3. I did notice that. Self dot data at 0 is X. Self data 1 is Y. And self data 2 is Z. Easy enough. Easy to understand. Return self. And then you could just have a public function 0 or something, which just returns you a vector 3 with a data element of vector 3 floating point 64, 0, 0, 0, and 0, 0. That'll return you your zeroed out vector. That's an easy enough way to implement this and this. What we can do is X, Y, and Z. So then, yeah, we'll create methods to do that. So we'll do pub function X F64. It needs to take in self, and the pointer can be constant. So because we don't want to we don't have a self. My bad. A pointer to a constant vector 3. And we can do return self.x because it will be returned as a value. Do the same thing, self, pointer to const, vec3, f64, return self dot y, and pub function z, self, pointer to const, vec3, f64, return self dot z. So we have an init version, we have a 0 version, we have x, y, z. So then there are some operators here. This is an indexing operator overload. Zig does not have operator overloads, so these will have to be named methods. So what we'll have is operator. So this is unary negative. So this just returns the negative of something. So what we would do, return it as well. It does, okay. I see what they want to do. They want to have chaining be a thing, so I'll try to support that as well as I can. So pub function negate would be based on x, y, z. Well, you just need to have a self pointer. In this case, it's not going to be that because you want to return a pointer to vec3 as that. So you will return self. And you would just say self dot data equals negative self dot data. And then what the next thing, the indexing I don't care about. So you already have XYZ to do it, and you could just actually pull the data element because this is public. So there's no reason for me to do that. And then there's just add equal. So pub fin add equal add eq, which takes the self pointer vec3, returns pointer vec3. So add eq would then just do self data plus or sorry, it takes in self and a vector. So it takes in another vector. That vector is the constant vector. So v is const vec3. I've done something here. I don't know what I've done here, but I've done something wrong. But I'm just going to do that for now. V data return self. Okay, I messed something up here. What is it? Self is a pointer to vec3. Next thing you need is another vec3, so that makes sense. Oh, right. There's no point to specifying it as being constant because Zig, when you pass this way, is always constant. So yeah, that was my fault. I wasn't thinking there for a second, thinking in two different languages. So you have plus equals, and you can add a negative, so there's no reason to do that. So we could do mul equals multiplication, takes an us and puts out another vec3, then spits out a vec3, so it returns self, and then we'll do self dot data times equal b data. There you go. So multiply equals, and then we'll also have a divide equals. So pubfin div eq self vec3 b vec3 and returns vec3. So self dot data div equals b dot data return self. And then next thing. Oh, these are by scalars. My bad. These are by scalar factors. So we'll do scalar. So scalar f64. You can't do that, but I think you can do splat. And I need to check what splat wants me to do. Splat makes a variable, produces a vector, element of the value scalar. So it's not v dot, it's scalar though. Yeah, there we go. That's why. And then same thing we'll have in here. So divide equals splat scalar, or yes, scalar. And this will become scalar, and this will be f64. There you go. Now we have SIMD acceleration for vector operations. So then we'll do pub function length, which returns f64, and it can take in a constant pointer to itself. Same thing with pubfin length squared. Self pointer const vec3 outputs f64. So then what we do is we'll just do return self data 0 times self data 0 plus self data 1 times self data 1 plus self data 2 times self data 2. And then what we'll do here is return return standard math square root of self dot length squared. And I believe that should work. We'll find errors in this. There's a note declared. Oh, that's because of this error passed the function shadows declaration somewhere. Tell me where. Init xyz. Oh, because it's the same name. XD, YD, ZD. That, okay, yeah, that's shadowing that. There you go. So now we have a thing that is happy with it. So now we have the vector functions. There's a binding here, and then there's some vector utility function. Got it. So the binding is just going to be another constant. So this will just be constant 0.3 equals vec3. So that's easy enough to create type binding. There's a printer. There's a way to do print formatting in Zig. For now, I don't want to necessarily do that. I want to look at each one. So then there's operators for doing add, subtract, multiply by scale. Oh, so multiply two vectors and multiply it by scalars. Okay, so these are the same functions, they're just outside, and you have cross product, dot product, and return the unit vector. These are actually very easy to do. So we can continue with this method. So public function. I can do the standard formatting one when we need it. I think you should be able to just use the normal print methods, which I guess I can just figure out soon enough. So we'll find that. But we'll do add. So we'll do self const vec3 or point const vec3. Yeah, that's. And then we'll do vector v. I mean, they're using u and v, which kind of makes sense here. Which is another vector 3. It returns a vector 3. And all we got to do is return u data plus v data. Actually, we return a vec3 where the data is this. Same thing with subtract here. So u pointer const vec3, v vec3, vec3, return vec3, data equals u dot data minus v dot data. Or does it want v minus u? No, it wants u minus v. That makes sense. Public function multiply. So multiplication here, I'm going to take u pointer const vec3, v vec3, returns a vec3, returns vec3 dot data equals u dot data times v dot data. Public function divide u pointer const vec3 v vec3 turns vec3. It actually looks like the div operation here is with a scalar. So v is actually a f64. So this is return vec3 where data is equal to u dot data divided by splat, or sorry, at splat of v data. And, or not v dot data, but v at splat must something have a known result type. Vector as at vector 3 f64 at splat. Now are you happy? It's happy now. Okay. So now it's happy. Public function divide 1 over t times that. Well, that's the same thing. Okay. Oh, that's an interesting one. Okay, and then you'll have the same thing happen with multiply. So there's public function multiply. Okay, we can't call it that. Mul scalar. Both of these are scalars, so div scalar and multiply by scalar. So u const 3 v f64 returns a vec3, return a vec3 whose data is u dot data divide or times at as at vector 3 f64 at splat v. So now we have a multiply and divide by a scalar. And I think that's all the operators. The only thing left is now just doing dot product and cross product. If you've taken, is it algebra 2? It might be algebra 2, it might be linear algebra, and it might be calculus 3. It depends. I don't remember what class you're supposed to learn this in. But the dot product is pretty much the sum of u times v, essentially, for each element. So the actually u.e, v.e, u.e, v.e, u.e, v.e. I think it's I think there is a way to do this. It's reduce, isn't it? Horizontal reduction with add. Yeah. This is actually transforms a vector into a scalar value of type E by performing a sequential scalar. Okay. By performing sequential horizontal reduction of its element using the specified operator operation. So v negative 1, v greater than, result is v greater than at as v at splat 0. Result becomes true, false, true, false. Okay. And then is all true is an and across all of them. Okay, that makes sense to me. So it applies the operation to each one. So theoretically, we can implement dot operator. So u const vec3 and v vec3 with and returns a float 64 result by doing result. Well, we could do at as, but I'll just do it this way so that the type checker can figure it out. Reduce dot add let me check that real quick. Reduce uses that and then what the vector. So then the target is now the vector that we need to change, and the vector that we need to do is u.data times v.data and return result. So what this does is it does u0 times u0 times v0 plus u0 times or u1 times v1 plus u2 times v2, and it should all do that using in one foul swoop. So one fell swoop, yes. And then the cross product, I don't think there's a good way of doing this one. Unfortunately, I don't think there's a good way of doing that in parallel. I think there might be like some, I should not say that because there's probably some crazy AVX instruction I've never read somewhere that does it all in one step. I actually don't doubt it. A cross product seems like something that would be useful. But let's just return vec3. Let's calculate each one. That's probably the easier one. For x, f64 is u data 1 times v data 2 minus u data 2 times v data 1. And it alternates like this for each one. So y f64 is u data 2 times v data 0 minus u data 0 times v data 2. And var z is going to be u data 0 times v data 1 minus u data 1 times v data 0. And I believe that's every pair. You have the 1 and 2 pair, you have the 2 and 0 pair, and you have the 0 and 1 pair. Now you have all 64, or all of them, sorry. You can return init x, y, z. Oh, what do you have to complain about? What did I do? Naming once again, xd, yd, zd, xd, yd. Yeah, having single letter thing, because it's shadowing something else I have. Color utility function. That literally just prints it. I'm not going to do that. Change our main to use both of these to calculate the pixel color. Is a color that is the result of blah blah blah. Is color also just like defined here as a vec3? It is defined as a vec3. Color 3, vec3. We're gonna have to create a method that actually calculates this. But then we're gonna use this color instead. Okay. Right, we can do that. That doesn't seem too bad. What we can do is we can create a color. We can do this, color 3, results from R, G, and B. And then we can do color.mul, multiply scalar by 255.999. Get rid of these, but we don't yet have a way of converting a color 3 to a color. So we should make a utility function here that does pubfin color 3 to color or something. It returns a color and it takes in a color 3. So you could even take a pointer to color actually, and you could do like you could do something weird with it. Yeah, I guess so. Yeah, that should work. And what I could do is do c dot pretty much we want to go to int from float to u8. So what we're doing would be we create a color. So we'll create color, which is a color, which is equal to color dot rgb equals rgb dot r is equal to at int from float, and then we can do color dot dx from float dy int from float. I know I misspelled it. C.z. Do that, and then we don't need to do anything. We could just return this. Also, that was a redundant typing there. Yeah, sure. Color 3 type is not a function. Color 3. Whoops. Yeah, it is not a function. You're right. Color 3. Oh, Jesus. That was not what I wanted to do. Color. Bar color. Color 3 init. That. Oh, it's called call. My bad. And then instead of this, we can do ppm.dataIndex equals color dot color 3 to color. Theoretically, that tests everything. Value of type main vec3. Oops. Color equals color. No index or field named color 3. That probably makes sense. I can understand that. Color 3 to color. You just pass in the color value. It's not that hard. Needs to be a pointer. Right. It's because it's find outside that it doesn't work. So no field named y in return self x, y, and z. Oh. My bad. Yeah, those are not self x, y, and z. This is self.data 0. Data 1 and data 2. My bad. Yep, and that works. And we should check it just to make sure desktop RT1 weekend and the test ppm works out fine. So we have a working demo with colors. Now we have the vector3 class for the most part done. And maybe I'll find a couple little bugs that I made there, but next part will be chapter 4. All right, welcome back, and we're now in chapter 4 of Raytracing in one weekend. So what we're going to be doing is raise a simple camera and a background. So the Ray class is going to be like the fundamental of Ray Tracer because you know it's in the name. So basically, the mathematical model of the ray here is pt equals a plus tb, and what this is a parameterized function p with a parameter of t, where a is the origin point, and b is the direction, and t is a scalar value multiplied by the direction. And basically, by changing the values of t, you can get to various different vectors or arrays at along this line. So pretty much, array is a function of having a vector that's an origin. So the origin vector is actually just the position. The direction is a true vector, I guess you would say. And pretty much, you want to be able to give a parameter t in to be able to figure out where you're going, essentially. So if we define this, it's pretty easy. Constant ray is struct, which is going to be there. And then pretty much all that we have is we have an origin point. So origin, which is a vector 3. I have a direction, which is a vector 3. And all we have is an initializer. So the initializer is going to take the origin and a direction, or it would be both zeros, which fine. And what we'll do is we'll do pub function init, and it will return a array. And pretty much we're going to create self, which is array. And we're going to take in two vector 3s. So we're going to take in an origin vector 3, and we're going to put in a direction vector 3. And the ray, actually we can just do this, return ray for origin, and direction. This type of constructor or this type of initialization, probably not necessary. I'm just doing it for the point of following along with like the tutorial. And then origin direction, I don't need methods for that. I just need to implement at. So pub function at, and then we'll have t, which is an f64, returns a vec3 result. So we're going to return the result of origin add direction multiplied by a scalar t. And this would be referring to an object of self, so I would need a pointer to ray. So then we would do self origin add to self direction multiplied by scalar. And if I remember correctly, multiply by scalar creates a vector 3 and add creates a vector 3. So yeah, we'll have a vector 3 result of doing at. Sending rays into the scene. Now that we were ready to turn the corner and make a ray tracer as core, a ray tracer sends rays through pixels and consumes the color in the directions of those rays. The goal steps are to calculate the ray from the eye through the pixel and determine which objects the rays intersects and compute a color from the closest intersection. When first developing Raytracer, I always do a simple camera for getting code up and running. You'll choose a 16:9 aspect ratio, which has this number, and we'll change the way that width is. I don't know if 400 over 256 is actually the right ratio. It might be. Oh, this is a new calculation. I see. So we're going to create the aspect ratio, which is going to be constant aspect ratio equals 16 divided by 9. Right. And then we'll set this to be, they're doing 400. I want to do 512. I feel like that's pretty easy. And the height would be image width divided by aspect ratio. So this would have to become a as f64 at float from int to convert that, and then divide by the aspect ratio, and then at int from float around the entirety of that expression, I think. And that should get you the right width and height. And if I check the output file, s.ppm, 512 by 288, yeah. I have no clue. Yeah, right. That's a 60 by 9 aspect ratio. If I like blew it up to full screen, it would eventually be full screen. So, yeah, okay, we got it to work. And there we go. Okay, so that's set there. Next thing is that they want to do is set a viewport height. Viewport image height. Image height is less than 1 colon image height. This is a really weird step because you know that logically it will never be. I mean, it could be less than 1, but at that point you just have a really big issue. I'm confused. Image height. Oh, they're using image height in a different way here. So if image height is less than 1, return 1, otherwise return image height. Height is less than 1. Yeah, this is just a case that's not going to happen. If for anything that's greater than 1 as a width, it will work. That's weird to me that they would do that. Now we need to have calculations for. I don't know if this is constant, so I'm gonna set it as this variable for the viewport height 2.0 and variable for the viewport width is viewport height times the image width divided by the image height. But if the wait, hold on, if the image width is divided by the image height, and the image height itself is the image width over the aspect ratio, what you end up with is image width over image width times aspect ratio. So what they actually just want is, wait, what? This is just times the aspect ratio. Yeah, that's not confusing at all. I don't know why this is the calculation. Maybe I'm wrong, but I did the math. It doesn't make sense. The ideal ratio versus actual ratio can vary on 2 of this. Okay, it wants you to just calculate it, I guess. So we'll do it. It's fine. As F64 at int from or sorry, F64 at image or at F64 at int or float from int image with divided by as F64 at float from int, and we'll do the image height. Sure, close enough. Rendered image should have that, so aspect ratio is ideal. Okay, next we will define the camera center, the 3D space from which all scene rays will originate. This is known as the eye. The vector from the camera will center from the viewport center will be orthogonal to the viewport. Correct. Yes. We'll initially set the distance between the viewport and the camera center point to be 1 unit. This distance is called the focal length. For simplicity, we start camera center at 0, 0, 0. We'll also have the y-axis go up and the x-axis to the right. Yes, this is how most people think of it. Negative z-axis points towards the viewing direction. 3D space has conventions. This conflicts with our image coordinates where we want to have the 0th pixel in the top left and work our way down to the last pixel in the bottom right. This means that our image coordinate y-axis is inverted, y is increasing, going down the image as we scan across the image. Start at the upper left pixel, 0, 0, and go down. So then they're going to do a correction. So we have this code. So now we're going to do the camera stuff. So this is the image code. Now we'll do the cameras. So constant focal length. There's no reason to make it constant in this case, because at some point we'll probably change it. So 1.0 viewport height is 2.0. The camera center is a vector 3, or a point 3 actually. Point 3 equals 0.3 actually. So we don't need to specify a type if we're literally giving it a type. Viewport UV, okay. Calculate the vector across the horizontal and down the vertical. Okay. So var viewport U is equal to a vec3 init with viewport width 0 and 0. Var viewport V is going to be vec3.init with the 0, negative viewport height, and 0. Okay, and then the viewpoint at the upper left camera center minus so that's sub the focal length. So this will be, oh, we don't actually have a splat method. That would be useful. Actually, this isn't a splat, so never mind. Vec3.init 0, 0 focal length. So we subtract that. Then with that result, we will subtract viewport u.div scalar by 2.0. And then we'll subtract viewport v.div scalar by 2.0 as well. Jeez, that is a crazy line. And then we'll do var pixel 0 location is a viewport upper left plus 0.5 times pixel delta. Oh, I didn't calculate the pixel delta. Whoops. Do that. So pixel delta u is viewport u dot div scalar at float from int. Jeez. Float from int image width and auto or var pixel delta v is viewport v dot div scalar float from int image height. And the at just got killed. Whoops. Now we have that. Now we have var pixel 0, 0 location equals viewport upper left dot add pixel delta u dot add pixel delta v dot multiply by scalar 0.5. Yes. Now, when we actually render to an image, we'll have to calculate the pixel center and then write the color. Okay. So what we'll do is we'll do the pixel center pixel 0 location plus pixel delta u dot multiply scalar by at by at float from int I location dot add ugh, such a big line. Okay, pixel location add pixel delta u multiplied by a scalar at float from int I. Okay, that closes that. That closes that. Add pixel delta v multiply scalar dot at float from int j. Pixel 00 location. Did I name that wrong? I don't know. Use of undeclared identifier. Pixel 0. Oh, I misspelled that. Whoops. Now we have pixel center. There we go. So now we have our ray direction equals pixel center sub camera center. Then we'll create a ray equals ray init camera center ray direction. And then we'll do well, we'll just have to get out a color. Yeah. So that will no longer be the valid code. Ray color. Okay, right. And then so var col equals ray color of all. Sure, and then we'll get ray color as being public function ray color results in a color 3. And it takes an array and then we'll just do return color 3. In this case, what does it return? 0, 0, 0. And then I want the color 3 thing to do the automatic conversion. So at int from float, we'll take this and we'll do just 2599. That way we can be more consistent about it when we do it. So there. This should render black. I don't actually have a thing open. Whoops. Stop. We can. Yep, it's black. Ray direction is a unit vector because it's simpler. Wait, ray direction is a unit vector? I guess so because it's 1.0. Yeah. So notice that in the code I did this. Now we'll fill in a ray color ray function to implement a sample gradient. This function will linearly blend white and blue depending on the length of the y coordinate after scaling the ray direction to unit length. Because we're looking at the y height after normalizing that, you'll notice a horizontal gradient, the color, horizontal gradient to color in the, wait, what? Because we're looking at the y height after normalizing the vector, you'll notice a horizontal gradient to the color in addition to the vertical gradient. I'll use the standard graphics trick to linearly scale 0a when a is 1.0. I want blue. When a is 0.0, I want white. This is 1 minus a times star variable plus 8. Yep, this is linear interpolation. So pretty much what we're doing is we're going to take ray color, is grab the direction, equals ray dot direction, and then we need to make a unit vector. Oh, dot unit vector. Oh, did I not make a unit vector method? I meant to. The unit vector is simply, I believe it's just divide by the length. Yes. Unit vector. Return vec3 data equals. Or actually, no. I can do something. I can do one better. I can do u dot div scalar u dot length. And that would be unit vector. So now I have the unit vector direction. So unit vector. Okay, so now we have the unit vector. And now that we have the unit vector, we can do the linear interpolation on it. So then var a equals 0.5 times the unit direction. So the direction y plus 1.0. And then we return. Okay, what's this? I see. Well, so now we have our color, which is, well, constant white, which is our color, and the sky color is that. So color 3 init const blue init, and what we want is white dot multiply by a scalar, which is 1.0 minus a, add to blue, which is multiplied by a scalar, which is a. Now we have a way of getting that. That should create the right result. If we go to our test ppm, we see that we get the same result. Exactly what we wanted. So that's it for chapter 4. Pretty simple chapter to get done. All right, welcome back, and this is chapter 5. So chapter 5, we're going to be looking at adding the first actual object into our scene, and that will be a sphere. So what we should do is, first off, we're going to start with the ray sphere intersection. A sphere is defined as x squared plus y squared plus z squared equals r squared, and you can tell that from the equation that x squared plus y squared plus z squared equals r squared, then that point is inside is on the sphere, and if it's less than r squared, it's in the sphere, and if it's outside the sphere, it's greater than r squared. So if we change that to be a set of coordinates, the coordinate system with an arbitrary point at the sphere center is cx y cz, so x minus cx squared, y minus cx, z minus cz. You can note that this is just going to be a point, actually. So you can do the point xyz minus c as the center point. So the point xyz minus the center point becomes the it becomes essentially this equation. So p minus c, or p minus c dot product p minus c becomes r squared. So this is the new vectorized version of the sphere. And then what we know is that P is the ray, so PT equals A plus T times B. We can expand the PT terms to be A plus T B, so what we should end up with ends up becoming TB plus A minus C because of associative property, I believe. And then basically we have two versions of the same thing. It's squared, so we get T squared B dot B plus 2T B dot A minus C plus A minus C dot A minus C minus R squared is 0. And that's how we can now figure out the calculation here. So A, B, and C in the quadratic formula, we B dot B, 2B dot A minus C, A minus C dot A minus C minus R squared. We get A, B, and C, and then we can calculate essentially ray sphere intersection. So to determine whether or not something hits the sphere, we can do public function, and what we'll do is hit sphere. And what we want is a center point to the sphere. So the center point of the sphere is a 0.3. So center is a 0.3. Then we'll need a radius, which is f64, and we'll need a ray that we want to be hitting. So this will be a ray. And what we'll return is a boolean whether or not it actually hits us. So to figure this out, we need to have a vector, which is the origin minus the center. So this is p minus c. So p minus c is var o equal oc equals ray origin. So ray dot origin dot subtract the center point. So now we have that. And to find var a equals the dot product of the direction. So we just need r dot direction dot r dot direction, if I remember correctly, and r here actually would be ray dot direction dot ray dot direction. Var b is 2 times the dot of OC and direction, so OC dot R dot direction, or ray dot direction. And then this result has to be multiplied scalar by 2.0. And var C is equal to OC dot OC minus R radius times radius. And then the discriminant is b times b minus 4 times a times c, and we return if discriminant greater than or equal to 0. And actually, I believe all these should be const. All of these can be const at least. And then now that we have that, we can do the ray color is if we hit the sphere from point 3 init 0 1, comma, the radius is 0.5, and we go with our ray. Then we can do return color 3 dot init 100. Save that. No field member named mul scalar in f64. Oh. My bad. Right. That should be times 2. That should, yeah, we're going down into that, so times 2.0. Yeah, there we go. And then we go to our files, desktop, RT in 1 weekend, open the test ppm. We end up with a red sphere in the middle, and it's pretty perfect looking. Look at that, we just made our first sphere. So, of course, this is lacking a lot of things, but we have ray traced to a sphere. So first, let's get a surface normal so that we can shade. The vector that's perpendicular to the surface point of the intersection, we have a key design. So to find something that's perpendicular, I'm pretty sure we're just going to use the cross products here. We also have a bug, I believe, well, where essentially if intersects the sphere by solving and finding a -1, it can have it behind the camera, and you can have an issue there as well. So, not exactly perfect. So you have center to the point, and the point minus center is this direction, and then you just need to find the perpendiculars here. So we can go ahead and make hit sphere turn into a different type of function. So instead of being Boolean, it's going to actually give us a floating point. And what we're going to do is that if the discriminant less than 0, we return -1. Otherwise, actually, we can. Zig has this feature where you can do return if -b or if discriminant is less than 0, -1.0, else returns -b minus standard math square root the discriminant divided by 2a. To a underneath. So this is b minus 4 b squared minus 4ac over 2a. This is the quadratic equation. So you have the quadratic equation as the result. Otherwise, you have that. And then so now we have bar b equals hit sphere point. So 0.3 init 0, 0, -1, 0.5, and we have a radius r. If t is greater than 0, then what we'll do is we'll calculate the normal n. So we'll do var n equals ray at the parameter t minus the direction, or the origin, sorry, vec3. So vec3 0, 0, -1. So vector, I think 0.3 makes it a little bit more clear what this is. This is the center of the sphere. So what we're doing is that we're taking the ray at here, and then we're subtracting. We're subtracting this point in order to then find the unit vector. So now that we have the unit vector, what we can do is we can return the color, which is going to be nx plus 1, ny plus 1. Frankly, color 3. Really what we want is actually just n add 0.3 init 1, 1, 1.0, or yeah, 1, 1, and 1. And then now that we've added 1 to everything, we just do multiply scalar 0.5. And r here is ray. Expression ray found constant ray. This can use a constant. It does not make a modification so that be runnable. No thing called dir. I think I meant to call it direction. Where did I use that? Where did I do that? What? Line 171. Oh. Yeah, that's meant to be direction. Go. We have a new image. And we get this color, which I think is the opposite of what I meant to do. Ray.at minus vec3 0 0 -1. I think the direction might be reversed of what I meant to do here. Let me see. Dot unit vector dot negate. If I negate the unit vector, that should give me the right colors, I think. Okay. Well, negate. I see. It should not negate itself, I don't think. I think I meant to do this, which would be return vec3, and then it would be vec3 return result of self dot data, or negative vec3 dot data equals negative self dot data. I think that's what I want. Yes, but not quite. Still, I have an error somewhere. Interesting. Okay, let me compare my methods here. Its sphere is ray origin minus the center, ray direction dot ray direction, 2 times the dot product of OC and the direction. C, dot product of OC minus radius squared. Discriminant is B times B minus 4 times A times C. Right. Returns, if the discriminant is less than 0, returns -1. Otherwise, negative B minus square root of the discriminant. Divide by 2.0 times A. And that gives me this, which makes sense because now I need to fix the place where I did the dot negate. If I run it now, there we go. We get the right picture. So yeah, the math error there was simply where this parenthesis was at the wrong location, which is still an error that could be made regardless of what programming language you use. Order of operations is hard. Don't worry. So we need to revisit the ray sphere function here. So now we have the notice how the equation for b has a factor of 2, and consider what happens to the quadratic equation if b equals 2h. So negative h plus or minus h squared. These observations, we can now simplify the ray sphere intersection code to this new code, which is ray origin minus center, direction dot length squared, because that is actually what the dot product is. It is literally the dot product of itself times itself. So now we have length squared. We have half b, which is OC length squared. Or sorry, which is the dot of OC and ray dot direction. My bad. And then the next one is half b squared. Wait, sorry. OC dot length squared, because OC dot OC is length squared. Minus radius times radius becomes half b times half b times half b times half b, and now there's no need for a, so it's just a times c. And then this becomes negative half b minus square root of discriminant over a. Negative half b minus square root of discriminant over a. This should return the same result. I should really just keep this image up in the corner here or something. Which results in the same exact thing, which is nice. So then we need an abstraction for hittable objects. So a hit record with a point, a normal, and a double T. And this can be of any function that it implements the same thing. So basically, we're making something that's kind of a trait in a way. And we just need a collection of objects with that are hittable in a way. So let's see. Easiest way of doing this: check a hit, and then you set up a record. So the record is the input, I assume. Yeah, record becomes the input, and you make that. Yep, and then minus p over radius. And then we have to figure out the outwards versus inward normals. Create a list of hittable objects. Then try to hit everything in the list. And then this is just reworking everything. And they added ground as a thing. So they made the ground a gigantic sphere. Okay, that makes sense to me. So we are moving to a different way of storing this data. So we have a structure called a hit record. So public constant, or well, constant hit record struct that has a point, the point 3. And then we have a normal, the vector 3. And we have a t value, which is the f64. And then we have things that can be hit. So we would have something with a function hit. And then we have things that implement that function hit. There is a correct way to do this. I want you to go back into the window, thank you. So there is the thing with allocator. If I go to the source of what an allocator is, where that's a vtable. I don't need a vtable. Although this is actually kind of correct. You just do alloc, the pointer, the context, and then the arguments after it. And depending on what the context is, receives the commands that you need. So we could implement this. Free alloc, free size, and pointer to yourself. An allocator. I don't know where allocator is first defined though. Allocator is self. Okay, that makes sense to me. So now we should define this is a type erasure to the allocator implementation itself. So we can do the same thing with a hittable. So we'll have a pointer, which is an any opaque. And then we'll have a vtable. And then with our vtable, we're going to define it as pub const structure. Which has simply the function that we need. So in this case, the function that we need is hit. So pub function hit turns a boolean. Sorry, hit is pointer to a constant function context turns a bool. Yeah, that makes sense. And what you need to do is you need to give it the context, the pointer to any opaque, and then you do length buffer. So then everything else after this, and then also has return address. That's return the end. So then everything inside of this is now the issues is exactly what we want. So array, and then we want a array underscore min, which is an f64. Array max is an f64, and we want a mutable pointer to a hit record. So hit record with a pointer to hit record. And const and deleted type array. And I meant not to do this, but I meant to do this. Now we have a vtable. Exactly what we need. And sub implementers are what happens next. So we now have that. Then we make a sphere. So const sphere, which derives from it, but it's let me try to figure this one out. This is a very complicated pretty complicated. Raw free. So we'll probably want to create a public function called raw hit based on the unit of self, which is hittable. A length. Well, no, not a length, but all the arguments and then the return address. Turns self.vtable hit self pointer and then okay. Ray, which is ray t min, which is an f64, ray t max, which is an f64, and hit record, which is a pointer to a hit record. And return self vtable hit self pointer, and then you pass in ray t min, ray t max, hit record, and the return adder. which is a raw hit, which is only meant to be called by the internals. And then, so everything that uses the raw can be called within side of self. Now I need to figure out how does that work in terms of I want an arena allocator or something. That should be easy enough to find. And create the allocator. You take the derived class, so sphere is derived from arena allocator. Or sorry, it has, yeah, it creates a child. And the vtable references back to here. Okay. Makes sense. Can be stored rather than the entire. The state is probably specific just to that. Child hittable. Hitable. There we go. That is hittable. Pubfin init. Oh, I see. This is a wrapper, that's why it has that. Pubfin init returns a sphere of itself, of course. Var sphere is var self is a sphere. And spheres have data, so we're going to get the sphere data. That's going to be a center, which is a 0.3, so that. And a radius, which is 64. And we're going to take in a center, which is 0.3. And we're going to have a radius, which is going to be the f64. Then we're going to take a center, radius, dot center equals center and dot radius. And then return that. Oh, sorry, return self. Not bad. And then it will define a hit function, which will do the hit stuff. So what I can do now is pretty much it would be using the same thing as like alloc essentially. Return address, which is free size and free is void, so it doesn't matter. Or everything seems to skip return address, so I'm going to assume it's not important for this method. Pointer, align cast, context. Yes, that makes sense to me. So, by the way, to get rid of this, we can just make it as simple as this. And we'll do a pub function hit, which needs to match the context pointer any opaque ray colon ray tmin f64 ray tmax f64 ray or hit record, the pointer to a hit record, and then return address, and it returns cool. That's just a bunch of pre-generated stuff. And then if you want to grab the actual thing, so the allocator, for example, of arena allocator comes out as pub function allocator. So I'm just going to do pub function hittable, which requires the reference itself. Wow, it's raining like crazy out there. And it needs a pointer to itself. And it returns the fact that it's a hittable. And it returns pointer is self and vtable dot hit equals leave has a comma here, and this has that. Now I have a hittable, which works. Now I need to implement hit, I think, as it seems that I just need to perform the actual function given the stuff that I have. So now here we go. What I'll do is vec3 OC. Oh, okay, so this is const OC equals ray origin sub center. Const A is our ray direction length squared. Const half B is OC dot ray dot direction. Our const C is OC dot length squared minus radius times radius. And then, well, okay, we'll need to know what center and radius are. So now we need to derive a member called ourself. So var self, and this goes back to arena allocator. This is how it works. Self, which is a pointer to sphere, equals pointer cast, align cast, the context. So that gives us that. So now we can do self center and self.radius times self.radius. Const A, B, C. Okay. And then now we have A, B, and C, and then we'll have a constant discriminant is half B squared minus A times C, and then if discriminant, if discriminant less than 0, we'll do the return false. Otherwise, we're going to find the square root of it. So auto var or const square root d is standard math square root of discriminant. And then now that we have the discriminant, we do root equals negative half b minus square root d over a. If the root is less than or equal to the ray minimum, or the ray t maximum is greater than or is less than or equal to the root. Is that really right? If root swap the locations. My bad. Yeah, so that's consistent. Equals negative half b for d over a. What? Okay, hold on. Am I tripping? Auto root equals negative half b minus square root d over a. Root is less than this or greater than this. Root is equal to what it literally is up here. Okay. And then if but we did not change auto root negative half b minus square root d. Oh, plus square root d. I'm tripping. Yep. Negative half b plus square root d. Okay. I missed that it was a plus versus a minus. If root is within the range again, so root less than or equal ray t min, or ray t max less than or equal to I didn't mean to do ray color. I meant to do root here, by the way. Root. And then return false. Yes. Okay. That makes sense to me. And then there's an error here somewhere. And then we'll do record. Hit record. Dot p is root. Hit record. Dot p is our at rec dot ray at p or at root, yeah. Then hit record dot normal is equal to hit record dot p minus center over radius. Hit record dot p point. Oh, whoops. Hit record dot point. My bad. Hit record dot point. Subtract center. Dot div scalar radius. And this would be self center and self radius. And this path is the return true path. Okay, that should work. Right. Am I missing something? It will tell me. It's return address. Yeah, we don't need that. We don't need that currently. So there we go. Okay, so there's a front face and a back face. The second design decision for normals is whether they should always point out. At present, normal will always be in the direction of the center to the intersection point. The normal points out. If the ray intersects the sphere from the inside, the normal points against the ray. If the ray intersects from the if it intersects from the outside, it points against the ray. If it is inside, the normal will point with the array. Alternatively, we have the normal always point against the ray. If the ray is outside, it points outward, but if the ray is inside, it'll point inwards. We need to choose one of these possibilities because they will eventually determine what side the ray is coming from. This is important for objects that are rendered differently on each side, like the text on two-sided pieces of paper, or objects that have an inside and an outside, like a glass ball. If we decide to have normals always point out, then we will determine which side the ray is on when we color it. We can figure this out by comparing the ray with a normal. If the ray and the normal face in the same direction, the ray is inside. If the ray and the normal face the opposite direction, the ray is on the outside. To do this, you use a dot product because the dot of the ray direction and the normal being greater than 0 means that they're in the same direction, whereas if it's less than 0, it's different directions. And if they're equal to 0, they're perpendicular. So yeah, we could do it that way to determine where the front face is of any ray. So what we can add to the hit record then is whether or not you're the front face. And this would be a Boolean. And you would have a public function set face normal, which takes in array and the outward normal. So we would be able to take in array. So we would need a reference to ourselves, and it would need to be mutable. So it needs to be a mutable hit record. And then we'll need array input, and we'll need a outward normal, which is a vec3, and it would be a void function. And then pretty much we would be saying self.frontface equals to r.direction so ray direction dot product with the outward normal is less than 0. Otherwise, it would, yeah, okay, so then we can say normal equals front face. So if self front face, then it's outward normal, else outward normal dot negate. And I forgot this. And normal here being set is self.normal. That makes sense to me. To add this to our hit function, all we need to do is add var outward normal equals hit record point sub self center by radius. So actually, wait a second. This is just var outward normal is equal to this, and then hit record dot set the face and the normal using outward normal there. So that gets there. We want a list of hittables. What we can do to get a hittable list. We could do pub const hittable or const hittable list equals structure. We would actually take the actual list as standard array list, which would be a standard array list of hittables. And we could just, yeah, we could say that's objects. Part of the objects that we care about, at least. And then we would have method, we can directly operate on it, so we don't need clear, we don't need add. And then we could actually have a method here called hit. What does hit do here? It takes array, does all of that to it. Okay, well. Right, okay. Full object standard array list. Hittable list is derives from hittable. Okay, I see. Paired pointers and vectors. So you just have a list. A hit record, which is a temporary record, hit thing. And you go over the array performing the hit. Makes sense. So then, hittable list, how does it actually get used? Do we just create a hittable list that's called the world? Yeah, we do. And we add the objects to the world, right? And that adds that. Okay. So we want to add, we don't just want to add a hittable, actually. We want to add the hittable and the context of the hittable. So if we wanted to make a sphere, for example, we would actually want the pointer to the sphere as well as the fact that it's a hittable. So, okay. So we would have the context. So objects, it would need to be a pairing of objects context. So we would need to make a hittable object structure to a context pointer. Context pointer to the pointer in any opaque, right? And then we would have the actual hittable, which is a hittable. That way we could always satisfy the requirements that we want, and then the objects is the list of hittable object. That makes sense to me. Okay, then we would want to construct that in place. So we're going to create a public function in it to create our thing here. So what we're going to do is we'll do public function init, which could return an error or return the hittable list. And we're going to need to feed it an allocator, standard memory allocator. The reason we're going to need that is going to be that we're going to ourselves the hittable list. We're going to set it to be undefined, and then we're going to actually set the self.objects standard array list of hittable objects dot init. And we're going to need to give the allocator into the self.objects object. So then we can add the hittable object. Right, so now we have a collection of hittable objects, and then we want to do this public function that is doing the hit itself. I do like that it inherits from hittable, but at the same time, it does not need to be. We can just have a function, public function hit, that is self, pointer to self, and then takes in array, and takes in array tmin, which is an F64, and array tmax, which is also an F64, and then a hit record, which is going to be a hit record. And then we'll be able to do that, and there's a bool. And then what we can do is that it's a pointer to self, and actually this should be a pointer to hittable list. And then what we can do is that we can create a record, so var record hittable or hit record undefined. We'll have a boolean, so we'll create a hit anything, the boolean, so boolean, or actually we can just say it's false, but we should probably make it clear that it's a boolean. And then var closest so far is equals to rate x. And then for all the objects in the list, so objects dot need to look at what an array list is. I think it's the items, correct? Items, yeah, items. So for all the items, item. Then you would call self objects items item dot context. It's context or hittable. The hittable hit. Give it the context that it requires. Ray tmin, ray tmax, hit record, and then return address. And this would be item to context, by the way. Item dot hittable. Raw hit the context. And then is hit. Aye, shit. Is hit. If is hit anything becomes true. Closest so far. Temp record. So record dot e rec equals temp is rec is temp rec. Oh, hit record equals to current record. So equals record. Hit record is record. Hit record. The contents of hit record is record. Tool is hit. Item hit, hittable. Raw hit. This. I expected semicolon. Oh, whoops. I didn't mean to. I wrote it in C format for some reason. A little too too much going on right now. Hit record that return whether or not hit anything was true. So now we have a hittable list. And then common constants, utility functions, sure. So we're going to create two spheres. Add them to the list. We're going to do the ray coloring function. Then we're going to do that. Okay. I think we got that. So what we'll do. So before we do the camera, sure, that's where we'll put it. We're going to do world. Actually, I need an allocator, so it will happen after I made the allocator, which is somewhere. It's somewhere, I tell you. Okay, here. Allocator. Render. And here is world. Okay, so we're going to create variable world is hittable equals hittable list dot init. We're going to give it the allocator. What we're going to do is we're going to do world dot objects. By the way, let's try. World dot objects dot append. Try that. Then we're gonna leak it for now. I think. No. Let's not leak it. We'll create. We'll fix it. We'll do variable sphere equals sphere one or sphere equals try allocator create and will be a sphere. And then what we'll do is sphere sphere.init. And what we'll do is sphere.init. We don't need to allocate it. We can just keep allocate it, to be fair. Equals sphere.init. And what we'll use is sphere.init. And I think that's asking for, we'll append a hittable object. Context is the reference to the sphere. The baseline here. Yeah. Context sphere. And we'll do the hittable is sphere.hittable. And of course, that's not what sphere.init wants. Sphere.init wants center point and a radius, right? So we'll do a center point. So vec3 center point. So vec3 init 0, 0, -1, 0.5. That's what we'll do. We'll do another one. Ground is sphere init vec3 dot init 100.5 -1 comma 100. And we'll do try world objects append hittable object context equals sphere hittable is, or sorry, not sphere, and ground dot hittable equals ground dot. Cool, we now built that. So then when we go into the ray color, we'll also give it the ray and the world. And when we go into here, we'll take a hittable list. We'll call it the world hittable list. And we'll go up here. We get rid of the hit sphere function. And what we'll do is we'll do a var hit record equals undefined. And then if world hit ray 0 infinity and give it the hit record, then we'll do return hit record dot normal dot add color3 init 111 dot mul scalar 0.5. I think that will work. Then okay. Error with non-void function with non-void return type implicitly returns. Oh, I didn't fix that. That's 259. Yes, return self. My bad. Next one is ray.direction const. Where? Whoa. 12. That's correct. Expected 2 arguments found 1. Two arguments found 1. Comp time t type for infinite on that, so 284. Infinite wants f64. Const main hittable list. Oh, it wants a pointer to it. That's fine. And then now let's go to 343. Sure, send that. It might be const correctness issue, but to main that hit record found, pointer to main that hit record. That seems like an issue. World.hit should actually take in a pointer, not a static. Right, this should be a pointer. That face. Member expected 5 arguments. Bounce. Uh, oh, I see. Give it a ray. I give it a ray T min. Ray T max. Give it hit record, and I give it that. We'll check that one later. 233 from here. Expected self hit record. Which array expected outward normal. Okay. 233 is just got to pass it the ray. And then this one is just the is hit fails. So that's at line 268. Hittable raw hit. Ray T min, Ray T max, hit record, return address. How do I define it? And self hittable. So it takes in a hittable. Oh, I didn't mean to do raw hit. I meant to do vtable.hit. Whoops. Where's raw hit? Item.hittable dot vtable dot hit. That's what I wanted to do. Pointer constant to pointer main hit record. Cast discards const qualifier. Wait, why is it const? No, that's a pointer to hit record. I want to pass the pointer to the hit record in. That ran. I got it, but not with the color. So something's wrong, but not super wrong. That's pretty nice. That's pretty nice. Feels a picture like that. Interesting. I wonder why that is. Hit record is undefined. Record. Oh, we're passing in this hit record. We want to be passing in our record. I think that's what I messed up. There we go. Oh. No, something's slightly off. What? Something is very close, but very slightly off. Everything refers to record. That makes sense. Hit record, record.t. Record. Yeah, okay. Hit record should not be. Okay. That's weird. Yeah, that checks out. I don't know why. Okay. Color spheres. Clearly, something with a depth is not quite correct. It might be this inside versus outside sphere question. So, determining whether the array is inside or outside the square. So if full front face takes in a self, takes an array, takes an outward. Front face is dot ray direction dot outward normal less than 0. If front face outward normal else negative outward normal. Let me check. If I reverse it, does it give me... Nope, nope, nope. That's definitely giving me the wrong side. So it's not that that's causing the issue. Okay, well, that's somewhat reassuring. Something very simple is wrong. It could really just be when I moved over the sphere hit code. It could be wrong. So sphere hit. Okay, so we grab ourselves. Sure. Ray origin. Let's subtract the center. Ray direction length squared. Dot of the OC and the ray direction. OC length squared minus radius. Yes. Discriminant half b times half b minus a times c. Greater than less than 0, return false. Otherwise, square root d is standard math square root discriminant. Root is negative half b minus square root d over a. Root is less than or equal to ray t min, or ray t max is less than or equal to root. Root is negative half b plus square root d over a. Root divide equal ray t min, or ray t max L equal root, return false. A record t is root. A record point is right at root. The outward normal is hit record dot point minus self dot center dot divide by the scalar radius. A record set face normal based on the ray and the outward normal. That looks okay to me. The hittable list record, hit record, is undefined. Hit anything, false. And the closest so far is the maximum possible distance. For every object, we determine whether or not something is hit by calling the hit function. If it's hit anything returns true. The closest so far is stored as record.t. And the hit record becomes temporary record. And then we return if we hit anything. The new hittable class does this. When we add things to the world, are we doing them in order? I might have a question of what happens if we do, instead of sphere hittable, ground hittable, do sphere here, ground here, and replace this one with ground, this one with sphere. Does it change the order? If so, that just means that we've iterated in a different... It does. Interesting. It does. It does. Order of which was added into the world matters for whether something gets hit before something else. That is surprising. Okay. That's all the answer I expected to see there. And then now we have an intervals class. That we use for the minimum and the closest. Okay, this makes sense to me. So we'll have this interval class. And we'll implement it then. So to implement, we'll do a constant interval struct has a max f64 and a min f64. By default, if we create an interval, it should be negative and positive infinity. I don't know. Infinity. That's fine in my opinion. Interval dot turn return interval. Ah, I see. Well, never mind. It has words for that. Pub fin empty, an interval. That is equal to return max is, or min, comma, max, minimum equals standard math dot max equals negative standard math inf f64 fin all. Also universe. Universe is everything. Okay. Sure, return dot there dot min equals standard math dot infinity f64 negative, and the next one is positive. Max equals dot standard math infinity f64. Yeah, makes sense. And then we want to see pub fin self pointer const. Cool. Pub function contains self interval and f64 x 4 returns boolean, returns min l equal x and x l equal max, and this is self min self max, and pub fin rounds is self pointer const interval x f64 bool, and then would be return minimum less than x and x is less. And once again, this would be self dot. And therefore, you can redefine the way that hittable works. Okay, somewhere. Instead of using const, ray t min, ray t max, we can do just a ray t, an interval. And then everything else we'll use ray t as an interval. And then ray t. And then this will cause an error somewhere else. In here, where we have ray t, which will be now an interval, which now demands ray t dot min and ray t dot max, ray t dot min. Or actually, yeah, this is more correct. Ray t dot surrounds root, or not ray t surrounds root, and not ray t surrounds root. And then now we have to change hittable list. So now we have ray t min, ray t max becomes ray t interval, and ray t dot max comes closest so far. Intervals instead takes ray t, and then here I change that, and then wherever we do world dot hit, Oh, it's somewhere in here. Ray color, right. And whenever we do world.hit, we do the interval between minimum equals 0, maximum equals standard math infinity. That should still work. It does. Okay, not too bad. I'm going to try and find why the ordering is mattering. There might be something very simple having to do with that. But yeah, I'll go ahead and try and find that out. So that's it for this one. We've went through chapter 5 and chapter 6 together. All right, welcome back. And this is we're going to be going through chapter 7, maybe chapter 8 at the same time. I was able to find the issue that I had. We have to add this line here to make sure that the record is only set if it's closer. So if the record T is less than the closest so far, therefore we're going to store the record there, because otherwise it stores in any order. So theoretically, if I change wherever I was set in the world, so sphere and ground, right now, if I do cd desktop and Zig build run, then I open get this result, and if we change the ordering, so instead of sphere here, we put ground here, which is what it used to be, and sphere here, and swap this one as well. There's probably a very easy way. I think I could have done YY and paste, and render it. It does the same exact thing. So behavior is consistent across, regardless of order. Now that that's done, we actually have what we need to do now is do a bunch of refactoring, and frankly, I'm not that good at NeoVim right now, or Vim in general. So I'm going to actually go ahead and set up the VS Code here, order to do the refactor. You'd rather not see me try to mess with it otherwise. Folder, desktop. Okay. So then that and minus time. This should be clear enough to read. So we can actually move things out into their own individual classes. So for example, I can make vector3 like its own class, along with like the point stuff, and the hittables. We could try moving out to separate classes. Let's see, what did they do? They have Ray vector3 as being independently, so Ray vector3 interval. So I guess we'll do ray.zig, and inside ray.zig, we'll actually define the ray. So what we can do is we can actually copy paste the insides of this. This is going to be the same sort of thing, but of course I need the vectors. So I need vec3.zig, or I guess I'd call it vec.zig, and we'll do that. And we'll take vector3, even this method here too. We can all put this in the vector zig. I think I'll need standard here, so I'll do const std equals at import standard. Everything else here should be pretty much normal language features, so I think there's no need to add anything else. So if I want to get vec3 here, I need to do const vec equals at import vec.zig, and then const vec3 equals vec.vec3. And also, I need to make sure that my declarations here, like this, are public. So pubconst, and add pubconst here as well. So now we have all public methods. So Ray should be set up, and then we can do we can create a ppm zig file, and the ppm zig file can have the RGB and the color value. Something. We'll throw that in there, and stuff will all go public again. So public on these. I think we'll need a standard here as well. This makes me remember that at the end here we have this color to color 3, or color 3 to color, sorry, and then what we want to do is const ppm equals add import ppm.zig, and const color ppm.color, and const RGB equals ppm. I think that should work for everything that we need here. And then we have hit record, hittable, both of which can be defined in like a hit.zig. And we can put hit record and hittable both in there. So we could do that, and then we could public, and we'll make this one public too. And really, all we need here is probably going to be. Oh, we also need interval. My bad, but we'll need we'll need const vec equals add import vec.zig, and we'll do const vec3 is vec.vec3. So I think that should get everything, and const 0.3 equals vec.vec 0.3. I think that's all we need here. We also need interval, so let me create an interval.zig file, interval.zig, and we can go out and find wherever interval is and take that out. In fact, I think that if we put interval.zig, the only thing that it needs is standard, so I think I can actually do this. And then I'll do constant SID standard. And what I can then do is I can say const interval equals at import interval.zig. That's how I can define interval. I don't think that needs an interval, and just this. So I think we're good there. Now, I did notice something about the way I implemented hittable list, is that it stores a hittable object, and hittable object has the context here. I forgot that in hittable, the definition of hittable, it actually includes the pointer as well. So I didn't actually need to store the pointer in hittable object. So I can get rid of a hittable object and just use hittable. So if I get rid of all references to hittable object, that becomes that. And I don't need to add a hittable here. I just need to do ground.hittable and sphere.hittable. So if I do that, my bad, I see it. There we go. Now we have an easier way of doing management here. And then we'll just do item.hittable. So now it would just be item.vtable and item.pointer to do everything. Then we can move hittable list. We can move hittable and dot list and the and this as well, which we might want to do into their own classes. So we can move hittable list and sphere into the hit.zig file. I could do something else, but I think that's fine for now. And then we need to group everything up. But first off, I know that this is going to trigger a billion errors, so I'm going to go back in and try to sort these out. So we don't have a declared identifier for rays, which I guess would make sense. So we don't know what a ray is. So we're going to basically be importing ray.zig. So a constant ray equals at import ray.zig. Hittable list wouldn't be known, so const hittable that import hittable.zig. Hittable.zig, yeah. And const hittable list is hittable list. The caller 3, so we would need to be able to get back that import vec.zig, and const color 3 equals vec.color3. A hit record, so const hit record equals that equals hittable hit record. Interval, const interval at import interval.zig. And then I'll have one at 25. So we'll need 0.3. 0.3 is just another variant here, so 0.3. Vec.0.3. And then we have vec3 as well. So const vec3 equals vec.vec3. Now we have one. We don't know what a sphere is, so hittable sphere. Then we don't know what ppm is, so const ppm import ppm.zig, and const ppm equals ppm.ppm. Then now we have a shadowed declaration, which is ppm out, and ppm out. Color 3.color is provided by vec, which should be able to do that. Now we're going to have instances, and it's not able to find hittable.zig. It's not hittable.zig, it's hit.zig. And then undeclared use of interval in interval itself, which is because const interval equals at itself. Or actually, it's at this, my bad. Here we go. And ray.zig doesn't know itself as well. Oops. Const ray equals this. That gets changed as well. Error use of undeclared right and hit.zig. Okay, and then in hit.zig, we need to check it out as well. Const ray equals add import ray.zig. What was the other one? Can't use identifier std. Oh, const standard import. And then the final one is hittable list is not marked as pub. It is easy to change. Just add pub here. And sphere is not marked as public either. So sphere is not public. So now we've done most of that, and then ppm member here. Sorry, where is this? In 83, save to file. Oh, yeah, ppm out. And then boom. So we've successfully refactored our application without too much fuss. And now it wants to move, the book actually wants us to move a lot of the stuff into camera itself. So I'll reopen Visual Studio Code. And we're going to be moving over stuff to a new file called camera.zig. And all we need is reference to main. So the ray color method is going to be part of the camera now. So I guess the camera is responsible for rendering, given a world. And then all of these other settings will probably be important. So I guess we can start with camera being its own standalone class, because it kind of is its own standalone here. And we'll move ray color over. And a lot of this will happen. So render is going to do its own thing. And then all of this is going to get station code in here. Then reduce.main should be. So to do the camera, let's start off by, well, we'll move the ray color method as part of camera. I guess now it will also rely on self. And we'll, we could call it camera. Do that. And then the next thing we would do is add all of this data. So what we need to do is pretty much grab everything from here. So we want to know the image stuff. We want to know the camera stuff. Calculate viewport stuff. Viewport upper location. So we could do that. Allocator we don't want to touch, so that stuff will go into camera.zig. And some of the stuff we should define on side, like this portion, can be defined outside. This won't change. Alongside of this stuff doesn't seem to change either, so we could declare these as constant as well. So focal length, viewport width. It just seems to matter that we have the okay, we'll have camera center. That one seems to matter. Actually, it might not. We might just need to have enough data to supply this method for the ray color and the render. Oh, for the render as well. So we'll have pub function render. And ray color actually is no longer public. So yeah, we'll do that. Self pointer camera void. And the render stuff all gets thrown together here. So we'll throw that into the camera.zig file somewhere here. And then our main file should have the allocator. Should create the world. I guess then we would create the camera, and then we would render the camera. So var camera equals camera init. And then camera render world. And as much as this makes absolutely no sense yet, we'll put this in constant camera equals add import camera.zig. So we're going to be shifting around all of the dependencies here, and getting it back to compiling. My bad. There we go. I'm going to quit and then reopen it just because it looked really glitched there for a second. I've had the same issue with ZLS. I don't know why. It's just the way it is. Build. I know it's not gonna work. PPM. Yeah. So the PPM changes that we made. We no longer need PPM here. We don't need interval here. We don't need hit record here. We do need hittable list. We do need vector 3. We don't need color or point. So I guess we'll need hittable. We don't really need ray. I think that's the minimum set that we need here. Then camera itself. Camera has no clue what point is, so const vec equals at import vec.zig const .3 vec.point3 const vec3 vec.vec3 const ppm equals at import ppm.zig const ppm equals ppm.ppm standards import standard render requires an allocator, so allocator and it needs pixel 0 location. Pixel 0 location seems to be a shared property, so we should make that actually a shared property. So pixel 00 location, which is a vec3 now member. So then we'll do var self is a camera, undefined, and then we'll set self.pixel location and return self. Oops. Now our next error is that this cannot be accessed because now self.pixel location equals self.pixel delta u and self.pixel v and camera center. So we will need the camera center, the pixel delta, so we'll need pixel delta u be a vec3 pixel delta v the vec3 and then camera center as another vec3, so self.camera center 0 point or uv, so self.pixel u and self.pixel v, that, and then self.center. So yeah, self.pixel v applied by a scalar, fine to me. It doesn't know what ray is, so let's import the ray. Ray equals that import ray.zig. And now it doesn't even know what the camera center is. Makes sense. So self camera center. And then it needs world. So world is a hittable list. So world hittable list. And ideally it should be a pointer to a hittable list. This would recall self.color. It also needs this. So we need to get a hittable list. So we need to import const hit equals at import hit.zig. Const hittable list equals hit.hittable list. Next thing is color 3 is not known. Color 3 is vec.color3. The next thing is hit record is not known. Enough to find const hit record hit record. Use of undeclared identifier interval, so const interval is at import interval.zig. And then now we need to go back out to main.zig. And then in here there is camera render, requires the allocator and the world. And then hittable list. So this needs to be a reference. And then error is ignored, so this should be try. This should run, and RT1Weekend produces the same output. So we have now successfully fully refactored the project, and the next part we'll do is the anti-aliasing. So you might notice that when you go into the image, which I just closed like a genius, is that this is a very small image. When you get in, you get these really jagged edges that are, okay, zoom in too much and it tries to make it like not clear, but there are jagged edges, and we need to do that. We need to get rid of those because those are very not nice. So pretty much what we have is that we have a pixel, but when you have a pixel like that, you get jagged edges. So if we do more than one sample per pixel with a slight random variation, we'll actually be able to get more information about whether it's like full or not. A lot of anti-aliasing algorithms, all they do is pretty much apply a blur based on how quote-unquote full the pixel should be. And now they add some utility functions here for random double and stuff like that, but I believe that's part of the Zig standard library, so I'm not going to. Interval now has an extra method called clamp, which I think is okay. So we're going to go to the interval class, or well, it's not really a class, but anyways, we can have a public function clamp, which takes itself, which is constant interval, and constant interval, and then we'll have x f64, and we'll return an f64. So if x greater than the minimum, or x is less than the minimum, return the minimum, else self.min, return min, self.min, else if x is greater than self.max, return self.max, and then return x. Very easy. Bright color can now sum all these together. So you need to pixel color samples divide by samples. Interesting. So writing out the color now looks at how many samples there were, which is fine, I guess. So what we can do in camera, we can define a variable samples. And what we can do is we can take out the color. So where we determine the color, there. So var samples. F64 at from int float from int self.samples. And what we do would just be pixel color, or sorry, the color that we got dot div scalar by samples, and this would be color equals color dot div samples by that. And what we can do is we can define var color as being a color3 dot 0, and then we do for 0 to self dot samples, we can just do this, and we can do color plus equals that. And what we should actually do, oh, it wants me to discard this. And what we should do in here will be var ray equals ray dot init. Oh, they're gonna add a get ray here. We can add a get ray function. It's fine. Var ray equals get ray. Sure. Pub function get ray. Self pointer camera I usi U32 and J is a U32. Okay. And we'll do that, and then we'll have it return array. And what we'll do is yank paste, yank paste. Oh, and that absolutely messed it up. Which, okay, it thinks that this is the right tabbing, which is not ideal. Okay, hold on. Tab, delete tab, delete tab, tab. Okay, and then pretty much we're getting the pixel center is equal pixel sample square ray origin center. Okay, well, we'll get rid of that. We have the pixel center. So we have the ray direction. And then we'll have var pixel sample square. So pixel sample equals pixel center plus pixel sample square, which we'll just call, I guess, it's a method. And then instead, so ray direction is going to be pixel sample minus the ray origin, which is the center. Ray origin equals self dot center, camera center. And then now we have that, and then we have the origin and we have the direction. So then we return array dot init ray origin direction. And we implement the function for sample square pixel sample square. Seems to just be autonomous and have its own state. So it's going to return a vec3. And what it does is it actually needs to be a member. Never mind, because it uses that. Okay, cool. So camera, it needs to be a member. So self sample square, sure. And then it will need a random, so var x negative 0.5 plus random. I don't know what random is. I'll need to find it. Plus random. And then return result of pixel delta u multiplied by a scalar times px x add pixel delta v multiplied by the scalar y. And then now we need to get the random, and I'll have to go find where random is. So we'll have random.random. And there should be cryptographically secure fast. We can go with the default PRNG. And there's the seed. Okay. And it's in it, and it's gonna give us back this Oshiro thing. I don't know. So we'll do random, and this will be a standard rand default PRNG. And we'll just do self dot random equals standard rand default PRNG init, and we'll give a seed of 0. That's probably the best we can do. And then what we can do is dot self dot random. So and then it returns a random itself. My bad. So then there's another thing called standard random, which is a name, all right. Init 0. Actually, I think we need to do rand engine. I think we should keep it on the stack at least. Default PRNG. So this will be the rand engine. And self.random rand self.rand engine. There we go. And it returns this random, and then we want a floating point within a range. So the floating point, actually, yeah, you can just do float and give an F64, and it will be in the range of 0 to 1. I don't know what range we're expecting here, but I think that's probably what this is. So plus, oops, there we go. Self.random.float, that would be F64, and this one will be self-random float F64. That works to me. Self pixel delta U and self pixel delta Y. That should actually do it. I might have missed something. Get ray. Yep. So this is gonna be self get ray IJ. IJ. Now the other thing we'll need color. Add equal. It might have a return as well. So it should add to itself. Analyze remaining. Oh boy. Did I make a infinite loop somehow? Self.samples. Oh, self.samples is not initialized. Whoops. That should be probably self.samples equals 10. That was a random number. Okay. That's better. That's better. Oof. I see. To be fair, now we can open it up. If we look at the edges, it's more dithered, which is the result. Well, okay, hold on. We can look into the side, and it's got that little more of a fuzzy edge there, which is due to the random sampling of the anti-aliasing. And that's it for chapter 7 and 8. All right, so here we are. We're back for chapter 9, and chapter 9 is diffuse materials. So now that we have multiple objects and rays per pixel, or so, yeah, we can make some realistic materials. First thing is diffuse or matte materials, and pretty much that's kind of like the default in a lot of engines. And pretty much what happens is that when you hit a surface, it spawns subrays that go out and try to intersect with other things. And it happens in a hemisphere pointing away from the normal. Essentially, what we want to do is we want to add some functionality to allow us to create a random vector and have that random vector point away from the normal in order to have that ray go ahead and actually intersect with something. If it goes through it, that's not exactly what we want. So we're going to have to add some functionality here to the way that both vector works and to the way that we're doing our ray intersection. This is where ray tracing starts to get a little bit more painful due to having to deal with everything here. So if we go into our vector class, let's go ahead and start by adding random vectors. So pub function random. We're gonna take in just the standard. We're gonna take in a random generator, which is standard random. It's gonna output a vector 3, and pretty much we're gonna return a vec3 dot init. That's gonna be random dot random, and I'm not sure is random double here. I need to check. Random double, is it from -1 to 0, or is it from? No, random double is between 0 and 1, or between a minute and a max. Okay. And I'm wondering, this is not between a minute and a max? Right. Oh, so we'll have two versions, one between the min and the max. Got it. So random dot float f64, comma random float 4 and random float f64. And this parameter shadows itself. That's a random engine. Right. There we go. Now we have the random engine. Next thing, we'll do public function random from engine. And we're actually going to take in the random engine random. And actually, we're going to do random range or random interval. And we can actually use an interval here. But we could do min. Yeah, let's do an interval here. Constant interval import interval, let's say. Random, and then interval. And it returns a vec3. And pretty much we're going to do a var vec equals random for vec3 that's 0, and we're going to have to apply arranged random. I think there's a thing to do this. Normalized exponential, just int range. Surprised that there's no float range. I guess it's not too bad to do float. So their code for random double, we'll just go ahead and use that here. So it would be interval minimum plus interval maximum minus interval minimum times random engine float for And that would be for voodoo vec data 0 yank paste, and then side here, yeah, do 2 and 1, and then just return back. And that looks good to me for the random intervals. Now we have methods to generate random vectors. And now we want to do one within inside of a unit sphere. Vec3 random from -1 to 1, length squared less than 1. Okay. So we can do random in sphere. There's a vec3, which is all true. Do we have loop? Nope. While true. Var p equals vec3 dot random interval. And we'll need a random engine, so random engine standard random engine, and we'll do random engine, and we'll do an interval dot min -1 dot max +1 if p squared less than 1, return p. So this needs to be within a unit here. I am kind of confused. I see. I feel like this is inefficient. Because when you're doing while true and doing this multiple times, you could also just do vec3 dot random interval. Same thing, random engine. And the interval is -1 to 1. But could do dot unit vector, and you could just return the unit vector. And that would be random within the unit sphere, because p length squared less than 1. It has to be, the unit vector is always of length 1. So I guess you would do technically multiply by 0.99, but I think the floating point rounding error should be enough to get you within the random unit sphere, or maybe sometimes slightly more. But the actual accuracy of being in the random sphere doesn't seem that bad. I think this is an inefficient method. We'll see. They have random unit vector. Oh, I see. So they want. Oh, okay. I understand what they want. I just don't understand why. Then they use a random unit vector. But why make this go to there? Random on hemisphere. It might be useful in another sense, I guess, but looking at this, I don't actually understand why you would do it that way. Maybe I've missed something, but now we do this with a random engine, standard rand random. And we also do this, I should really have just imported rand, uh, with a normal, so a normal, which is a vec3. And this outputs a vec3. So var unit is equal to vec3.random in sphere. And then if, so we do unit dot with the normal, and it's greater than 0, return unit, else return unit negates. So actually this is just return if unit there, do this, else and I'm sure it'll do negate. And random engine is a required argument here. There we go. Okay. And then we're gonna change the way it works in the point guard. That's been solved. And then we're going to do ray color. We're gonna do if world.hit. We're gonna grab a direction. vec3.random on hemisphere, and we're gonna give it the self.random engine, and I should rename this to rand_engine, which I will do. And what we'll do is rand_engine, and then we'll do the record, hit record dot normal. And then now we have the direction, so it would be scalar 0.5. Oh, this actually becomes more ambiguous. So this becomes return ray color, which is self.raycolor, using a new ray that is from hit record dot point, comma, direction. Well, do dot origin and direction. So we now have the ray from origin to hit point to direction, with given the world itself. And then we would do dot multiply by a scalar of 0.5. That now no longer discards itself. That's good. Up, and it decided to put it all back into one line. That's great. So theoretically, no rand_engine. That's fine. I just prefer using underscore here. Then no field rand or rand. Oh, right. Need to name this also to rand engine. And now that we have it, we got rand.random found Ransa Shiro 256. Do we actually want to pass it there? Oh. We don't want to pass the rand engine, actually, we just pass the random itself. Okay. That rendered a lot slower. But theoretically, desktop. Yep, we got a grainy looking image of our actual output result. The first render on a diffuse surface. So The issue is that sometimes there will be too many bounces or too many subchildren. Yeah. And we're going to basically need to give it a maximum number when we do the ray coloring. So what we'll do is we'll define a max number of max children. Yep. Max children is a U size. And self max children is 10, let's say. And then we can do render. And now in we can go to ray color, and it takes ray and the world, but then we're also going to have the depth. And the depth itself is going to be the size. And pretty much if depth 0, return color 3.0. And then we're going to change the one to be random on hemisphere, ray color, and then this will just be depth -1. That way we have a recursion limit. And when we do color at equal up here, we'll give it self dot max children. And that cuts down the render time quite a bit. And we have this very pronounced looking shadow, actually. That's kind of interesting. So that kind of indicates that maybe our method isn't quite working correctly. It might have to do with either a random interval itself. So we can try using this method. Then I actually know where we could try doing that, which doesn't seem to actually slow it down that much. Look, that's the same result. So it might not be that in itself. It might be actually having to do with the interval. Interval min plus interval max minus min, random engine float. So we did add something wrong here. We should be able to have a random double and 1. Makes sense. Random in unit sphere. Sure. And a random unit vector. Then you get a random unit vector. You dot it with a normal, either the unit sphere or the negative unit sphere. Very quite interesting. Set the main function to depth limit. They set to 50. I still get this weird looking shadow. So something isn't quite perfectly normal. Because if I look at it, the sphere paints a picture this way. And it's not perfectly around it. Maybe perhaps it could be the little bit of code I added extra to determine the hit direction in hittable. And maybe that's the issue, but I don't think it is. That doesn't seem to produce a different result there. Interesting. I could round and sphere. Would re-render it like that, but that still doesn't fix the issue. Okay, cool. Or I could go back and re-enable the code I just disabled. Which renders correctly. Weirdly, we've got this strange ray, like cone, that is causing an issue. We've wound up with getting something that doesn't really make sense. Doesn't seem to be a fundamental issue with this. Maybe it's a fundamental issue with a range. So interval minimum plus interval max minus min times random engine float. That is weird. That is extremely weird. That we get such a sharp cone. Like, that's a very sharp cone of rays. I will continue on for now, but that's very concerning. So then there's a shadow acne problem, and they're allowing 50 depth, so I guess we're gonna have a 50 max children. Still pretty fast. Then we'll do world.hit r comma interval. So the interval's from 0. So by adding a little bit of depth to that, by doing 0.001, should fix the issue. Fix some of the issues at least. And indeed, it does make it lighter. Oops. It does look a lot better. Still, the diffuse is still wrong. The diffuse should be in every direction, not just the normal direction. So maybe my normal calculation might be off. Although, no, we do get out the normal correctly. I do change it back to being based on ray normals. Record, hit record dot normal. Dot normal. Then I get the same error that's outside of bounds. I messed that up. I messed that one up a little too much. I mul scalar 5. Fix it. Now it should be within the bounds. And we get these as normals. So the normal direction correct. So random on hit sphere on hemisphere. It may not be 100% correct here. Random self ray color, barter. You get this. And I think, yeah, the only thing I can really look at is the vector class as being the problem in here. So, I mean, if I follow their code to the letter, well, not quite to the letter, you know, but we have random, which is just straight up random doubles from 0 to 1. We have random range from a minimum to a maximum. The interval minimum, the interval maximize minimum times random engine float 4 times, or 3 times rather. Then we have that, so then we need to figure out how to manipulate the random vector. So in here, we can do this while true random in sphere less than 1. And we'll look at interval minimum is -1, minimum is 1. Return p. And then we could do random unit vector. Returns vec3 and requires a random engine as well. Did random. Return random in sphere with engine and get the unit vector of it. Then we can fix the random on hemisphere method to look exactly like what they wrote. So var on sphere is to vec3 dot random unit vector with the random engine. If on unit sphere dot normal greater than 0, return on unit sphere, else return on unit sphere dot negate. And the updated result looks the exact same, so that doesn't fix it. It could be that the randoms are not correct, so we could do standard debug log, debug print, and there, and vec data 0, vec data 1, vec data 2, and I'll need a new line here too. We could find if these are all a lot of negatives, there's a lot of positives. We've got positive numbers, we've got negative numbers. I don't know if it's an even distribution. Maybe we don't have an even distribution. Maybe that's the issue. Maybe we need a a normalized distribution. So there is float norm, which is an option. So with a normalized distribution, could be getting bad results. And also, please stop printing. That's gonna get very annoying. They're slowing down significantly. And that fixed it. Whoa, that actually fixed it. So random is not by default normalized. That is the issue. That is very strange. Okay, and then we can probably replace this with these two methods with the random interval to unit vector, because random in sphere should run correctly. That actually makes it a lot better in terms of runtime, and this is a much more correct looking result. There we go. So float isn't normalized. That's an interesting thing to know. Is that there's no normalization function, which I guess is technically not specified. It says evenly distributed, and we want one normally distributed to look correct. And that runs pretty well. And by the way, this is not with d optimize equals release fast. It might be even faster, but it will take forever to compile too, which is valid. It's way faster. Wow, that is significantly faster. Nice. So now we have ray traced spheres, and we have them with no shadow acne. And now we need to implement true Lambertian reflection. Scattering reflected rays evenly produces a nice soft diffuse, but we can do better, more accurate. Is the Lambertian distribution. This distribution scatters reflected rays in a manner that is proportional to cosine theta, where theta is, I'm assuming this is theta, where theta is the angle between, it might not be theta, but yeah, where this is the angle between the reflected ray and the surface normal. This means that a reflected ray is more likely to scatter in a direction near the surface normal and less scatter in directions away from the surface normal. So the change is actually fairly minimal. So the direction that we choose for the scatter is a random unit vector. And so, and rect.normal. So that looks like all we change is this. To varder equals standard, or hit record dot normal dot add vec3 dot random, not on hemisphere, but just random in sphere. And random in sphere wants self dot random. Get this result, which that looks interesting. Record normal. Random in sphere vector. That doesn't change. That's not the result I got. Okay. Direction is just a random unit vector, so vector3 dot random in sphere with a rand engine for self dot random, my bad, dot unit vector add, which I think random in sphere is already the unit vector result, which it is. Interval unit vector dot add hit record dot normal, and theoretically that's supposed to be what we get, but that is not what we get at all. And I really can't get how it's supposedly tinted more blue, supposedly. But I really don't understand the unit direction, ray direction unit vector, a equals 0.5 times direction y plus 1, white and blue, 1.0a, and a. Yeah, I really don't get how that could work out this way. Do we need to normalize the so hit record dot normal dot unit vector as well? That could make sense to me. Even then, that doesn't change the image. I don't know how they've done this. Why does it give this result? Cell bug, use shadow, no shadow acne, cosine theta, p, and there's normal surface n at the point of intersection has exactly two sides as the normal. At the point of intersection at one sphere, so they use the function random unit vector, which, just to be clear, random unit vector is literally random in unit sphere dot unit vector. Vector direction, gray color. Okay, well, we can try doing. Go back to trying this method, but I don't think it works. So, while true, var p equals vec3 dot random interval, and we give them the random engine, and we give an interval. Actually, we could just do anonymous because it's easy enough. Minimum there, maximum's 1 if p dot length squared plus 1 return p. Sure, and then we could do subfin random unit random in unit sphere random engine standard random vec3 just returns vec3 dot rand in sphere random engine dot unit vector, and inside of here the random in unit sphere, and We'll do random in unit sphere. It gets slower over time. I thought it was interesting. This gets it correct. Because this is... That doesn't make sense to me. I don't get how that is correct. Hit record.normal. Okay. So, what is the difference? Okay, that's confusing to me. I don't understand it. If someone in the comments could explain why that changes it, I'd be glad to understand it. That does not make any sense to me. Now we can do gamma correction. So that sounds pretty simple. We're going to do 0.1 times ray color. Looks the same. Oh, I see what they mean. So it's just how much the factor is. Okay, that makes sense. So 0 is pretty dark and light is pretty light, and it's not even because this is pretty dark, this is pretty dark, and this is very suddenly light. So they want to do linear to gamma. So what they want to do is apply linear to gamma, the square root of a linear component. Which makes sense. Because if you do the square root on everything, it's not possible to ever get it's not possible to ever get above 1. So we could do standard math square root on these. So standard square root and standard math square root. So we'll just add that and that. And by doing that, it slows down so much. We get very dark results. Oh, it needs to be before we do the multiplication, not after. My bad. Using this gamma correction, we now get a more consistent ramp from darkness to lightness. There are 2 spheres, dark to light. Yep, that looks way better for 0.5. And that's it. We've hit the end here, so that's pretty good. I'm very curious on why it takes seemingly longer every time we do a random floating point distribution. I feel as though perhaps the default method of doing random number generators may not be super fast. There's quite a bit of different random number generators. So we could definitely try and fix that. For now, it's okay. I just wonder why the performance is the way it is. Although I think it still runs reasonably fast here. So we're good on that. Anyways, thank you, and I'll join you with the next chapter tomorrow. Alright, welcome back to the Raytracing in 1 Weekend series in Zig. And right now we're going to be continuing chapter 10. I was able to find something inside vector.zig, So the floating point normal distribution was causing a lot of performance issues. When you change floating point normal to normalized regular floating point with the true Lambertian reflection model, it does create similar images like this. This is at 1280 by 720, and it operates relatively quickly. So the entire thing renders in 0.9 seconds, which is quite fast. So simply by changing that, we're able to get a lot more performance out of the application. Also changed it to be 1280 by 720, although we can go back down to our previous sample size of 512, which we'll rebuild here and give similar results. So without that out of the way, we're going to go ahead and start working on metals. And metal here has an abstract class for the materials itself. And we're going to have to do the similar thing to the way that Hittable works with the vtables. So first thing we're going to do is probably going to be creating a brand new file and saving as source/material.zig. And then standard equals import standard. And pretty much I want to copy the same exact idea. So const material equals structure. The pointer, which is any opaque, and it also has the pointer being the context. I might have called it pointer. So let me go ahead and hit .zig. Hittable has a pointer, okay, and a vtable, which is its own vtable. So we define vtable as its own structure, and we'll also make sure that it possesses one of these structures for vtables. And then we would also need this to be public, so it's exposed. And that method should have a virtual Boolean scatter. So this will be a method. I want to get rid of that tab. There we go. So we'll create a method. So scatter is a function with, or a pointer to a constant function with the input and output of a bool. The input is going to be array, so that's going to be array. Oh, so it has an input and output. So we have array in, which is going to be array. It's going to need a hit record, so we are going to have a record, which is hit record, which I'll need to import. And then we're going to have a scattered output, which is going to be the array. And this should be a pointer, so that's mutable. And then comma here. Ray is not defined, so const ray equals add import ray.zig. And const hit is import the equals import hit.zig. And then const hit record is hit.hitRecord. And now we have defined that, and our LSP crashed. So let me reload that real quick. This sometimes happens with ZLS. It's just kind of a factor of life. They're working on making it more stable. So, okay. So we now have sphere. So inside of the hit, I have hit record. We're going to add the material. We're going to do const material, or const material equals add import material.zig, and uppercase material, material.material. And inside of the hit record, it will have a mat, which is just a material. And then we'll need to add material as part of the definition of a sphere. So going down to where the sphere is defined, when we initialize it, we'll also need to give it a material. So material, or whoops, not here. Sphere. Yes. We'll give it a material. And we'll have it have a method or an instance of the material here. And then dot material works fine. Save. Something is incorrect here, but that is potentially unused, I think. It.zig call here. It might be that this is public. Let's see what the compiler says. Shadow's definite. Oh, shadow declaration. My bad. Oops. I didn't mean to do that. Const. We'll call it mat. Instead. This will be mat, and dot mat equals mat. There we go. And then when we do this, we'll go to record material. So hit record mat is self.mat. So there we go. Now I have a way of using materials. So now we should create our Lambertian material. So we'll create pub const Lambertian material structure. And the Lambertian material should have a function material, which returns an instance of material, which returns anonymous dot pointer itself. Itself is pointer to Lambertian material, and a vtable where dot scatter equals the scatter method itself. Let me check exactly how I did this in Sphere. I'm pretty sure. Okay, equals the method name. And also we're gonna need that context pointer to the any opaque. So it's gonna be context pointer any opaque. Scatter equals scatter, which is not yet defined. So we'll define a public function scatter, which has context pointer any opaque, and that has the ray in, which is ray, and have a record, which is a hit record, and a ray out, which is going to be the ray, pointer ray, and a boolean. We'll do that. Now we have a valid way of doing scatter. We'll also need to define a color that it uses as its albedo component. So albedo is the color 3. And we don't have color 3 imported, so we'll have to go to const vec equals add import vec.zig. Now that we have vector, we'll get the vector 3 component, or the color 3 component equals vec.color3. And now we have a way of taking a color. So then we'll do a public function init. This is more for API purposes. You could just direct instantiate this, given that the constructor is so simple. But we'll give it a color 3 input and give it a Lambertian material output, var self, or actually just return Lambertian material containing albedo equals color. Like that. So now we have a method there. Now to do the actual scattering, var scatter direction equal to the record normal dot add vec3 dot random unit vector. We'll require a random engine once again. So we'll probably need to amend this method given random engine with standard random. Same thing here. So before that, for scatter, we'll need the random engine as well. Asking the random engine is kind of nice because it allows us to really customize what the random engine is rather than being tied down to one. Vec3, and then this is going to be random engine. And vec3 is not imported, so we just got to do const vec3 equals vec.vec3. So now we have that. We have scatter direction. And then the output array, so the ray out, not array, but ray, ray out pointer is equal to brand new ray with dot origin equals record point, and direction is scatter direction. The attenuation, which is the color. So there's a color attenuation here. Oh, I missed that somehow. I think. Random engine, ray in, record, hit record, and then a attenuation, which is a pointer to color 3. Scattered, which is a pointer to ray. Okay, whoops, that's 2 outputs. And then we'll need a pointer to the color 3 output called attenuation. And then attenuation is going to be the albedo. And then the final thing I think is returning true. And albedo will be self.albedo, so we'll need to get self, which is equal to add pointer cast at align cast of the context, and this will be a pointer to Lambertian material. I forgot the add there. Then we'll do self.albedo here. Now we have that. I don't think we took the original ray in, I think. Yeah, R in does not match here. So we now have a scatter material. Next thing is vector3 method called near 0 that returns true if the vector is very close to 0 in all directions. And I guess this is done because floating points won't necessarily always equal 0. They'll be very close to 0, and you have to do that. Here.init will expect 30 arguments. I'll fix that later. So we'll need to add a method to vector3 for determining whether or not a vector is near 0. So public function near 0 takes in a vector v, which is a constant vec3, and returns a boolean if. So it'll define const s, which is -8, which is, I think, valid. And then you can return standard dot math dot fabs at vector data 0 is less than s, and standard math fabs, which is floating point absolute e1 is less than s, and standard math fabs e2 is also less than s. And e1 and e2, sorry, our vector data for both of these. My bad. Vector data. There we go. Now we have a method of checking if something is near 0. So then we can catch degenerates here. So if auto scatter direction, so once we do that, if the scatter direction is near 0, then the scatter direction is equal to the record normal. Very nice. So then there will be mirrored light reflections, because if you have a polished metal, it reflects what it's if you have like a metal ball, you look at it, kind of reflects a little bit of what's nearby it. So we can do light reflections off of it. So what we'll have to do is create a vector method for doing a reflection, which will take in 2 vectors. So the public function reflect will take a vector v and a normal vector n. So pointer const vec3 and just a vec3 for the normal. Returns a vector 3 will be return v.subtract the dot product. Okay, so we're gonna do the dot product is equal to the dot product of v.n times 2.0. And that becomes a scalar, and then we want to do n multiplied by the scalar d. And what we want to do is return vector v subtracting this dot product. And then the metal material will reflect it that way. So it wants us to create another material called metal. Structure. Takes in the color as albedo as well. Color 3. The function is basically the same, so pub fin init call color 3 turns metal material, turn metal material dot albedo is color. Very easy. And we'll also create the function material itself, pointer to metal material, returns the material, so returns the pointer is self, and vtable is scatter will scatter. And currently we don't have that method defined yet. Public function scatter takes into context, which is a pointer to an any opaque, and then need the random engine, standard random. We'll need ray input, which is going to be the ray. We're going to need a record, which will be the hit record. And then we'll need a attenuation. So we'll do attenuation, which is a pointer to color 3. And then we'll have the scattered. So scattered is going to be a pointer to the ray. Or this could be ray out, actually, is a pointer to array. And it should return a boolean. That's what I forgot to do. And then what we'll do is var reflected equals vec3 dot unit vector, or random unit in random on hemisphere in sphere in unit sphere. Let me check that one real quick. Oh, is it called random unit vector? Am I? Nope, that's not what it's called. This is an error as well. The random unit vector function gets you random, not in hemisphere, but in unit sphere. In unit sphere. Random in unit. It's true here. Random in unit sphere. Give it the random engine. And we want to do dot reflect it based on the ray normal, which is hit record, or the record normal. Now we have the reflected. Now we want to do for ray out, pointer is equal to ray dot origin is record point, and the direction is equal to the reflected vector. Then we do the attenuation is equal to self albedo. How do we get self? We do var self pointer to a metal material equals at pointer cast at align cast the context pointer. Now we have self albedo, and then we can return true. And ray in is discarded once again. So then now we go to the ray coloring method, which is in the camera class. And then we find ray color. This is in here. And then if world.hit, we're going to create a new ray called the scatter. So var scattered is going to be a ray, which is undefined. And var attenuation, this is color 3. Attenuation, which is a color 3, which is undefined as well. Then we're going to take if the hit record that got successfully there, so hit record dot material vtable.scatter with hit record material. Okay, well, let's create a temporary binding here for no, it would be constant. Mat is hit record material. So if mat vtable scatter mat dot pointer comma the record, so ray dot it needs to be given the ray that we got, that we sent it. So that's ray. Then we would need to give it the hit record, reference to attenuation, and a reference to scattered. Then we'll do that. Otherwise, we would return a color that was 0. So what we'll do here is return. What we'll take next is we'll have the next color equals ray underscore color given the scattered with depth -1, and pass on the world. And I'm not sure if I need to pass anything else. Yeah, I don't. And this would of course be self.rayColor. And then now that we have the color, we would do return call dot multiply by the attenuation. Of course, we still have the error in main, is that we did not define a material. So what we can do is we can define materials. So let me do that. Const material import material.zig, and then we'll also do const. We'll have both the Lambertian material.Lambertian material and const metal material.metal material. And I think I have not made it public, even though it should be. Yep. Need to make this public now. And then go back. So we'll create a material for the ground. Actually, well, before we create the world, let's do material. So we'll create a var mat ground is Lambertian material init from color 3 dot, or we can use a vec3 init 0.8 0.8 0.0. Mat center is Lambertian material init from a vec3 0.7 0.3 0.3. Material left is metal material init from vec3 init 0.8 0.8 0.8. So that's like a gray. And material right is material metal material dot init vec3 dot init 0.8 0.6 and 0.2. So it's like a reddish orangish color. And then we'll create 3 spheres. So we'll do sphere. So the ground will now need the material ground. So mat underscore ground. The center one will do mat underscore center. And then we'll need to do var sphere L and R, which is sphere init vec3 init 0 0 or -1 0 -1 0.5, and then mat left. And then var sphere right is sphere init vec3 init 1 0 -1 0.5 and mat right. Now we'll just do try world objects append, and then we'll do sphere L dot hittable, and we'll do the same thing, try world objects append sphere right dot hittable. Now that we have a full world of stuff, we're missing something else. Expected type material found material dot Lambertian material. Right. So these are all need to be mat center dot material. Dot material attribute. And then expected 6 arguments found 5 mat vtable scatter. And this is in camera.zig 110. Oh, I think I missed the random engine, so that might be the issue. And where is this 110? Mat. So before the ray, it should be self.random. I believe. Zig build run. Doesn't crash, which is a good thing. And we got like these 3 materials here. These seem more reflective though. I'm interested in. And clearly we have like slightly different variation. Material on the left does not seem to be like reflective at all, which seems odd to me. It is made with a metal material. So it is made using the metal material. I really am interested. Why is that the case? Maybe a computation here in scatter that's incorrect. So in here, we have a scatter method. Is going to take self, sure. Reflected is random in unit sphere. This is not what the code says for the reflected material. That's probably the actual issue. So var reflected is equal to the unit vector of r in dot direction. So random and the ray input. So ray input dot direction needs to get turned into unit vector, and then needs to be reflected using the hit record. So the record dot normal. That's how it gets determined. Then undeclared. Use of undeclared identifier engine. There we go. And then if I do this, now it gets the correct reflections that I believe we're supposed to see. Still has this weird like acne pattern that I think is from the random engine. If I do go back and go to the way that we're deriving randoms and change it to actually, let's see, does it change if we do optimization equals release fast? I wonder if that changes how, yes, it does change how it works. So the debug build doesn't have the same random number generator, which results in different looks here. Although mine looks a little bit more noisy, I think maybe it's because of that. Attenuation protection is 0.001, or the shadow acne prevention thing, which should be in camera.zig, where when we give it the minimum, we give it 0.001, maybe 0.01. There's a little bit of an experiment here. That might be causing some of it, although that doesn't appear to be the majority of it. It could also be because of the sampling. It just doesn't look correct. A little bit too noisy in general. The next thing they added to material is the fuzziness factor. So whenever you have a metal, it's not always perfectly reflective. And I should just use the build run. Whenever you have this, it's not perfectly reflective like this. So what we would expect to have is that there's a bit of matteness, M-A-T-T, matteness to it. So we can go to the materials. We can change the way that we create the material. It has a fuzziness factor called fuzz, which I think would mean F64. And then we give in this material F is an F64. And dot fuzz equals if f is less than 1, it's f, otherwise it's 1. So that's just a clamp, actually. I don't think we did a clamp method. Maybe we did. Oops, and then I wanted to find clamp. Not here, so I'm just gonna do the if statement here. So if f less than 1, it's f, else it's 1. Easy enough to do that expression inline in Zig. And now Lambertian, oh, that's not supposed to be in Lambertian. Whoops. That was meant to be inside of metal. Wasn't reading the thing I was putting it in. fuzz f64 dot fuzz equals if f and 1f else. Now it says metal material expects that, but we have to go into here, so we need to go scattered. So now we have a reflected. That's the same. Then we'll do the ray output scattered. Ray with the origin point equals record.point. With the direction reflected added to a random unit vector, so vec3.random in unit sphere, given the random engine, multiplied by the scalar self.fuzz. And there we go. So we'll run. And then we still need to go ahead and add fuzziness to our materials here. So if we go into main and we change the mat left and right to 0.3 and 1.0, we get kind of this fuzzy looking reflection here. So there's a metal spheres with fuzzy reflections. It's pretty nice. And then what we can do here is we can produce a nicer image by going up here and doing the image width is 1280 by 720. And then we'll have the samples be 50 samples and children be that many children. And this should be slower. So build-d optimize release fast. Extra compile time will definitely help it run faster. It does have this slowdown effect, which is interesting. Did I go back to float normal or not? I am a little bit unsure of what the random generator is. But in this case, we now have a very high quality looking image of a fuzzy kind of material here and a very matte looking material. But this one's more reflective, obviously. So yeah, we have successfully completed chapter 10. All right, and welcome back to chapter 11 of Raytracing in one weekend. What we're going to be doing is the dielectrics, which basically just means a clear material that has both reflection and refraction. Some things are water, glass, diamonds, etc. And it splits into being both reflected and refracted. One gets transmitted through it, the other one gets transmitted out of it, essentially. So basically, we have this entire thing where we have ray reflection, and basically, let's go ahead. First thing, the refraction is going to be described by Snell's law, which is n times sine theta equals n prime times sine theta prime, where they are the eta and eta prime. Okay. Are the refractive indices. Typically, they have different indices depending on what everything is. Air is 1.0, so it goes pretty much in a straight line, etc. And it's described by this equation, r prime, where you have r of perpendicular plus r prime parallel, which is eta over eta prime, and then r plus cosine theta n, and r prime perpendicular or parallel is equal to negative the radical of 1 minus r prime perpendicular squared times n. And then we know the value of every term on the right hand side except for cosine theta, but the dot product of two vectors are this a, b cosine theta. So we can restrict a and b to be unit vectors. So therefore a dot b equals cosine theta. So now pretty much we have a r prime perpendicular is eta over eta prime times r plus negative r dot n times n. And then this is the function that we use to calculate it in the vector class, which is what we're going to open up here, vector.zig. And we can put it under the reflection. So we'll do a public function, refract, which is going to take in a constant, a vector, uv, which is pointer to constant vector 3. And then we'll have n, which is a vector 3 input, and we'll also have eta I over eta t, which is going to be an f64, and it returns a vector 3. So to do this, we need to get the cosine of theta, which is standard math floating point minimum f64 min, of the dot product of uv dot negate dot with n and 1.0, and whichever one is smaller becomes cosine theta. R out perpendicular, so R perpendicular equal to eta I over eta t times the unit vector added to cosine theta times n. So n dot multiply scalar by cosine theta gets you this vector, and you need to multiply this by eta I over eta t. And then the R out parallel becomes the standard negative of standard math square root of standard math floating point absolute 1.0 minus R out perpendicular length squared. And then this is just a scalar factor, so n dot n multiplied by this scalar. So equals n multiplied by scalar over standard math. Now that, and then return R out perpendicular added to R out parallel. And that is how we define a reflection. Now, oops, I didn't mean to quit. We can go into material and create a brand new material. So pub const dielectric material is a structure which will have the index of reflection. Index of reflection is an f64. So the function in it takes in index of refraction, not reflection. Fraction. IR, which returns a dielectric material. So far, self, which is a dielectric material, undefined, or actually return dielectric material with dot index refraction is IR. That's all you need to do. Then we'll have a public function called material itself, which is a pointer to a dielectric material, and you return pointer itself. I think I want to add comma here and a comma here, and dot pointer self comma dot vtable equals dot this and this will do a scatter function as scatter. And this will return a material object itself. Most part, and then we just need to get define our function for scatter. The public function scatter takes into context, which is a pointer of any opaque. It takes a random engine, standard random. It takes in a ray in, which is array. Takes in a record, which is a hit record. Takes in an attenuation, which is a pointer to color 3, and it gives out a scattered, which is the pointer to the ray output, and it's a boolean. And essentially what we want to do is we want to say attenuation is equal to color 3, 1.0, 1.0, 1.0, so it's white. And then the refraction ratio is record.frontface. So if record.frontface, then it's 1.0 divided by self IR. Otherwise it's self IR. And self isn't defined very well here because I haven't added necessary code. And that's the same code here. Flexion ratio. So the unit direction is going to be the unit vector of ray direction. Refracted is going to be unit direction refract based on the record, normal, and the refraction ratio. Scattered is going to become a ray. Origin is record point. Direction is refraction direction, so refracted. Turn true. So then Balanced dielectric material is material, dielectric material. And what we want to do, center and left will make those dielectric then. Okay. We get this as the result. And actually I'm going to modify the camera class, because I believe I changed my image size, yeah, to make this faster. Big build run. Color 3 is not a function, but no field named IR. IR is refraction. That's probably a change to the vector, I guess. Yeah. I think it's supposed to find the minimum. Jesus. There we go. That was a bit of a process there to fix that. And what we get is identical to the image here where we have the two on the left doing the like upside down refraction. That definitely doesn't look right. The ray material with the higher refractive index, there's no real solution. There's no refraction possible. If we refer back to Snell's law and the derivation of sine theta prime, we get sine theta prime is n over n prime, eta over eta prime, times sine theta. So sine theta prime is 1.5 over 1.0 times sine theta. If the air is inside this glass, outside is air, the value of sine theta prime cannot be greater than 1. So if the equality between the two sides of the equation is broken, a solution cannot exist. If it does not refract, therefore it must reflect. So in order to fix this, we have to change the way that the dielectric material works. So once we have determined the unit direction, we are going to calculate the cosine of theta, which is the minimum between the dot product of the unit direction negated dot record normal and 1.0. For sine of theta is standard math square root of 1.0 minus cosine theta squared. Var cannot refract equals the refraction ratio times sine of theta being greater than 1.0. Var direction, the vec3, which is undefined. If it cannot refract, then the direction is equal to vec3, the unit direction reflected with the recorded normal. Otherwise, it is refracted, so direction equal to the unit direction refracting the record normal, and given the refraction ratio. So now we have a thing that determines whether or not it should be. So then ray becomes the origin record point, and the direction is equal to the direction code. Expected statement found up. There we go. And that should give us a result. Oh, we also need to change the materials before I show you that. Material for the center. Material ground 0.8, 0.8, 0.0. We're going to make this a Lambert material here. So it's a vec3 in it with 0, 1, 0, 2, 0, 5. This is dielectric with 1.5. So we get this put here, which shows exactly what we want. Glass sphere that sometimes refracts. So then now real glass reflectivity varies with the angle. So we have to add some code here be determined based upon the reflectance. So what we would need to do is we would need to add more code to the material here. Which is a public function called reflectance, which takes in a cosine, which is an f64, and it takes in a ref index, which is f64, and returns an f64 result. So var r0 is equal to 1 minus the ref index divided by 1 plus the ref index. R0 equals R0 times R0. Return R0 plus 1 minus R0 times standard math power of 1 minus cosine the fifth. And that's what I want to do. And now we have a method to calculate reflectance. So, or the reflectance of cosine theta and the refraction ratio is greater than a random number. So random engine dot float f64. Big build. Expected 3 arguments, found 2. I assume the first argument is probably what are you raising to the power of? Yep. So if we run it, we now get this. Oh, and then we need to interesting trick with dielectric spheres. So that if you use negative radius d geometry but the surface normal points invert inwards, this can be used by making another sphere at that location. So let's try doing that. And basically we're going to make a sphere L inner. So var sphere L inner equals sphere init. And we would need to do vec3 init -1 0 -1 with a -0.4 and mat left. And we should be able to get out the same result, but we're not getting the same results, which might indicate a small issue with our calculation. Let's go back. Oh, I did not add the sphere inner. That's part of the reason that it doesn't work. Try world objects append sphere L inner hittable. Now if we rerun it, we get kind of the correct result. It is interesting that it's not exactly correct. Part of this might be due to the way that the debug version of the random number generator works is different. And it kind of helps, but it's not quite correct. So let me check exactly what the issue is. There is in material. Reflectance is calculated for R0 equals 1 minus ref index over 1 plus ref index. R0 is R0 squared. R0 plus 1 minus R0 times power of 1 minus cosine to 5. This is fine. If cannot refract or reflectance of cosine theta is greater than random engine dot float f64, then this happens. Which seems right. Also, I think they changed the material right has a higher reflectiveness. That's what I thought too. Um, Metal material, it's not 1.0, it's 0.0. We go ahead and reopen this result. We get this, which looks a bit better. I'm thinking that maybe I've changed the limit here for the camera to have a max of this many children. If I change it back to being a higher amount, I'm thinking that this might fix, yeah, it does fix the issue of the internal bounces that can occur in here. So we do get the correct looking result from that. And we have these two like little reflections. Very nice. So that's it for doing the dielectrics. We were able to manage to get this chapter done. Next one we'll just be doing the camera stuff. So we'll be doing both positioning the camera and the defocus blur. All right, welcome back. We're going to be doing chapter 12 of Ray Tracing in one weekend. And in this section, we'll be doing the positionable camera, being able to point it, to place it, and give us an FOV. And pretty much we'll be able to change how things look. I'll also be doing the defocus blur, which is like basically a little lens or depth of field blur, as you can see. And then maybe at the end I'll even do the final render as well to conclude the series. So to begin with, we're going to change the class camera itself to take in parameter, and the parameter is going to be the vertical field of view, VFOV, 64, which is 90. And then when we're determining the viewport the viewport dimensions, what we can do is modify this so that we can calculate theta, which is equal to degrees to radians of VFOV, which is, if you don't remember, 90 divided by 180 times pi. So, and then we can calculate the actual height, which is the tangent of theta over 2. And just to be careful, I'll call it height. And then we'll take the, does height shadow? I think it does. I think H shouldn't shadow. And then viewport U, or viewport height, rather, determined on this. So actually, the right place to put this is up here with the constant. So what we'll do is const focal and then const viewport height and then constant theta. And F64 is equal to VFOV divided by an 8 times 3.1415, or standard math pi. And then constant H equal to standard math tangent theta over 2. And then viewport height is then equal to const viewport height is equal to 2 times h times focal length. There we have camera dimensions. I'm going to do 2 touching spheres. So do that. We'll take var, I think it's constant r, F64 standard math cosine on standard math pi over 4. And then material left and material right are both going to be Lambert materials. So Lambertian material. And then we'll init it with a vec3.init, and color will be 001 and 100. So var mat right is Lambertian material init with a vec3 100. Now that we have that, we can do two spheres. Material left, material. The initialization is -r0, -1. This one will be positive r0, -1, r, and at right. Then do sphere L and sphere R. I missed a comma somewhere. Oh. Oops, run. Didn't mean. Here we go. But you got the same result as here. So to position and orient the camera, you have a look from to look at point. So we have 2 points, which is look from and look at. So in the camera, we'll define constant point. So look from equals 23 init 0 negative, oops, 0 -1. We'll define a look from a point look at equals 0.3 init 0, and you'll need a vector that's up, which is vec3 dot init 0 1 0. And then we'll need to form the basis vectors. So we'll have u as a vec3, w as a vec3, and u, w, and v vec3s. The camera center now is the look from point. The focal length is now going to become focal length f64. Going to get moved down. Actually, or we could try and promote that. So its focal length f64 is 1.0 by default. And move that here. What we could do for the focal length is going to be look from dot subtract look at dot length. That'll be the focal length is the distance there. And then calculate the vectors. So we can do calculate self dot w equals look from dot sub look at dot unit vector. Self dot u is the cross product of v up and w across w, self dot w. And self dot v is across, so it is self dot w crossed with self dot u. And then the viewport underscore U and viewport underscore V are now viewport with times U. So let's yank these. Oops. I thought I yanked it. Oh, I did. I just missed where I did it. So we have W, U, and V. And then viewport U becomes self.u multiplied by the scalar of viewport width. And viewport V is self.v multiplied by the scalar of negative viewport height. And viewport upper left is self.camera.center subtracted by focal length times W. So self.w multiply scalar by focal length. Let's see. Self camera center minus W times focal length minus viewport U over 2 and viewport V over 2. Change back to the prior scene using the viewpoint. So VFOV 90 look from is -2 to 1 0 0 -1 0 1 0, and then change back the main function where we had mat left. So we'll have var mat ground equals 113 material init vec3 init 0.8 0.8 0.0 var mat center Lambertian init vec3 init 0.1 0.2 and 5. Mat left and right are changed, so this is a dielectric material. And it actually has an inner as well. We'll add, and it's 1.5. And we'll have mat right, which is going to be metal material init, vec3 init of 0.8, 0.6, 0.2, 0.0. And then we can get rid of R. And then what we can do is define our world. So var sphere, or var ground is equal to sphere dot init of vec3 init 0, -100.5, 1, 100, material ground material. Then we'll do a sphere, which is just center. So sphere init vec3 dot init 0, 0, -1, 0.5, and material center material. For sphere left is equal to sphere init vec3 init -1, 0, -1, 0.5, and material left dot material. For sphere L inner is sphere init vec3 init is going to be -1, 0, -1, and the size is -0.4, and it's material left material var sphere right is sphere, init vec3 init 1 0 -1 with 0.5 and mat right material. And then what we want to do is world dot try world dot append or world dot objects dot append ground try world ground dot hittable try world objects append. So ground dot hittable, we'll do sphere dot hittable try world objects append sphere left hittable try world dot append sphere right hittable and try world objects append sphere left inner dot hittable. I believe that should be every object, and if I render it out, I should hopefully get it from a different perspective. I wonder why the scan lines are so slow. Part of this... Oh, we're looking at a slightly different angle than I thought we were going to be looking at. Probably just because I missed a number somewhere. -2 to... Look from -2 to 1, 0 0 -1, 0 1 0. That's interesting. 0 -1 -2 2 1. We get the like top down point of view. By changing vfov down to 20, we should zoom in. So let's check if that code works. Or checking where the direction is supposed to be. I think we've made probably just a small error in one of these calculations. Yeah, that zooms in. So we're missing a small calculation here. So we have look from, look at, and we have v up. Center is equal to camera center is equal to wherever look from is. That's correct. Focal length is look from minus look at dot length, which is true. And then W is look from minus look at dot unit vector. U is equal to unit vector cross, cross of VUP and W dot unit vector here. I think that's what I missed. And cross WU. Times U times negative V. That might be the issue. Really chugging to try to do this. It's closer, but it's not turned. So probably viewport UV is the next thing to look at. Viewport U is U multiplied by the scalar width, and viewport V is negative height times V. Which is fine. Pixel delta is divided by the scalar. Fine. Oh, we're also doing 100 samples. Let's do 10 samples. Viewport upper left is camera center subtracted by self.w multiplied by the scalar focal length minus sub viewport udiv scalar and sub viewport v div scaler. And self pixel locations viewport upper left plus 0.5 times pixel u added to pixel v. Everything else looks correct. Let's zoom out and do 90 FOV again while I try and find what. So we have -221. Oh, 221, not -1. That's why. Yep, there we go. Works. Perfectly fine. That was my issue. Yep, there we go. We got the exact same zoom in look there. And we can even do a render that I'm going to save here. At higher settings here, where we do 1280, and we'll do 100 samples. Render optimize equals release fast, and that way we can run really quick render. It's not even that like bad when you consider how fast it is. Relatively, it's gonna slow down in this area because there's just more ray reflections going on. Final feature is the defocus blur, which is that depth of field sort of approximation of a thin lens. Yeah, if we scale in, this looks a lot better. I'm just gonna save as a document test3 PNG because I've just been saving these. There we go. Now we have an object. So we don't need to simulate the inside of the camera. The easiest way is just to figure out we have a lens and we need to figure out at what point do we get out. So next thing we need to do is add a thing to a vector to create a vector with inside of the disk. The disk is representing the lens. So random in unit disk, and we're going to need a random engine. The pointer, or not pointer, just a standard random. And it returns the vector 3. So we now have this. So we're just going to, while true, var p is equal to vec3 init, and we're going to be doing 2 randoms and a 0. So it's going to be -1 to 1. So it's going to be this code with filled in. So var p equals vector 3.0. Oops. There we go. Instead of vec, it's p data. The minimum here is -1. The maximum is 1. So 1 minus -1 is 2. So now we have p data. It's just 2. Then yank, paste. Thing happens here, 1, and the other one can be 0. So then if p length squared plus 1, return the p. So we have a way to get a thing inside of the unit disk. Then in camera, we add 2 more parameters. So this is going to be a constant. The focus angle, which is an f64 is 0, and constant focus distance, an f64, which is going to be 10. And we're going to create 2 vec3s, which is the focus disk u and the focus v. we can get rid of focal length, it appears. And viewport height becomes the focus distance. And then viewport upper left now, instead of using focal length, uses focus distance. And now we can calculate the defocus disk. So defocus radius equals focus distance times standard math tangent of degrees, so defocus angle over 2 divided by 180 times standard math pi. And then self defocus u is equal to self.u dot multiplied by the scalar of defocus radius, and same thing with self. Defocus disk v, self v multiplied by the scalar of the defocus radius. Not angle, the radius. And now we go to the ray angle, or the ray origin, which is in the get ray. So we want to do this, have that. So in get ray, when we determine the ray origin, so if focus angle is less than or equal to 0, it is the center, else is self.defocus disk sample. We'll do for that is we'll create a function defocus disk sample, which takes in self, which is a pointer to camera, and it gives back a vector 3. And pretty much var p equals vec3 dot random in unit disk, and it returns self dot center dot add focus disk u dot multiplied by the scalar of p data 0 added to the self defocus disk v multiplied by the scalar of p data 1. And focus disk here comes from self. Making sure that the other one comes from self, yeah, it does. I didn't mean to I didn't mean to run like that, but it should work, I guess. And I think it should look exactly the same. Given that currently we aren't we set it as 0, so it shouldn't really set anything. Things it wants us to run at is defocus angle of 10, distance of 3.4. So let's set that up. Focus angle of 10, distance of 3.4. And what we get here doesn't really look any different. Vec3 has a random in unit disk. Comes from somewhere. And this needs to get self dot right. No struct, nothing called center. No field name center in self dot center, self dot camera center add. Oh, didn't mean to do Q, but okay, that seems to have worked. Go back to camera. There we go. Now it's running, and we should get the defocus effect. Ooh, that's a little bit too much. I think it's because we're like zoomed. We're definitely a little bit far out. And also I'll reduce the sample count for now. We're doing above 9. Defocus angle is 10. And defocus is 3.4. Reevaluate. Changes here. The focus radius. Well, check viewport height real quick. Height is just 2h times focus distance. Fine. The next one is viewport upper left. Is self W multiplied by scalar focus distance. Fine to me. I think we might have an error in defocus radius. The defocus radius is equal to the focus distance standard math tangent of degrees to radian the focus angle over 2. So var f half is not really even a var, it's const def half equals focus angle over 2, and const def rad is def half divided by 180 times standard math pi, and then def rad is used here. So tangent times defocus radius, and defocus disk u is self u multiplied by the scalar of defocus radius, and multiplied by the scalar of the focus radius. Also, the ray origin is if defocus angle is less than or equal to 0, self camera center. Otherwise, self dot defocus disk sample. Defocus disk sample takes a random unit disk. Does. And then self self camera center add self focus disk u times e dot data at 0, and adds to defocus disk b e data 1. Looks good to me. So that should actually set it up correctly. And then the final render is this code. Will do. Still getting a little too much here. If I increase the distance, say 5.4, that doesn't seem to help. Very confused. What? A little bit extreme. The angle, yeah, the angle definitely seems to be wrong. Is it possible that the tangent, that's actually, I didn't even think about that. It's definitely possible that the tangent just wants you to take defocus angle over 2. Focus angle It's possible. I don't think it's supposed to happen that way. It should become worse, not better. If that's the case. Oh, yep, that definitely looks worse. What is math tangent? Same as calling at tan. In radians, okay. Tangent of the focus angle to radians, so the focus angle divided by 2 divided by 180 times standard math pi. Still very bizarre to me. I mean, at least it shows up, right? Defocus angle, defocus distance. I feel like the distance field might even be less. This is a really weird issue. Nope, that doesn't help. Okay, let's check the vector real quick. While true, vector 0. Vector is between 0 and 1 times 2, so 0 and 2 plus -1, so 0 and -1. Same thing happens in p data. If the length squared is less than 1, then p. That's fine to me. Defocus angle. Okay. Is set to 10.0 and set to 3.4. Then viewport height. This is 2 times h times focus distance. Okay. Viewport upper left. Camera center minus self.w multiply scalar focus subtracting viewport u over 2 and viewport v over 2. Defocused radius radians sure is the focus angle divided by 180 sure times standard math pi. And put in defocus radian here. 10. And our defocus radius equals focus distance times standard or tangent of focus radians over. Does it matter if the angle is over 2 to begin with? I don't think so. Can go back to the top if it doesn't look better. Worse. What is the returned value? 1.745. 0.1745 times the focus distance. Then if I do divide by 2.0 here, beforehand to return the same result. It doesn't return the same result. Returns a smaller result. That's interesting. Defocus angle over 2 divided by 180 times pi. Is that number instead? Which makes it even blurry here. Oh, great. Oh, great. Really, this is a difficult one. I don't think this will change it. Oh, there's a panic. Part of floating point value is out of bounds. Oh, okay. I wish it would tell me what the value was that it found was out of bounds. Yeah, that would really help. Standard mass square root. The axis out of bounds. Problem is I don't think that actually makes it out of bounds. Although, okay. Let's say focus distance. Oh, here's a good question. Where is the pixel sample? Ah, I think I found it. It's here. Ray direction is minus pixel sample minus camera center. But in this case, it's actually minus the ray origin itself. That should run faster. There you go. That's the correct result. It was subtracting the wrong area. Wow. That took a little bit too long to debug right there. I'm not going to lie. All right, so now we have code to actually render out this blurred image or deblurred. I don't really know. Defocused. That's what I would say. image. And then now we have this, so let's make the final render of the tutorial. Material ground. Sure. We could leak memory here. It doesn't really matter too much to me. Well, we still need a world equals double list init the allocator. Ground mat is virtue material dot init and vec3 init 0.5 0.5 0.5, and then var ground is here initialize with vec3 init. Zero negative 1000 0 1000 ground mat dot material. Then world dot objects append, also try world objects append ground dot hittable. There we go. Now we have that for a doubled for loop here. A comma B, okay. For 11 B var match choose for camera random float move the camera here. There we go. So we have the mat choose var center equals vec3 dot init at a plus 0.9 times camera random float f64 comma 0.2 comma b plus 0.9 times random float f64 if center dot sub vec3 dot init for 0.2 0 dot length greater than 0.9. Then create a material, and then we'll make a sphere. Okay. Okay. sphere, well, the sphere itself is going to require the sphere can actually occur after this. If mat choose less than 0.8, Beto is literally a random. So vec3.random. And then mat virtual material in it with the color. Allocator create routine material try at dot star routine material init material equals at material. Else if mat chooses less than 0.95, call is vec3.random, except random interval and we need to pass the camera random. I forgot about that. And here camera random comma interval min is 0.5, max is 0, bar fuzz vec3 is camera random load f64 times 0.5, and then mat is try allocator create metal material at dot star equals metal material dot init, and we'll use cull, not color, cull, and we'll pass in the cull and the fuzz. And material is mat dot material, then else class, so mat is try allocator create dielectric material at dot star dielectric material dot create dot init with a value of 1.5. Material equals mat dot material, and then now that we have that, we create sphere if mat this probably needs to be called actually color. Okay, and then var sphere equals try allocator create there then sphere dot star equals try equals sphere create from center raise 0.2 add material, and then now that we have the material being used, we do try world objects append sphere dot double. Doesn't know what a material is. Yep, that's what I want. Undefined interval. Okay. Const interval. Interval.zig. Size cannot represent a negative integer value. Whoever said it needed to be U size. Okay, well, var a could be literally anything. Equals negative 11 while a is less than 11. A plus equals 1. Var b, I32, negative 11. While b is less than 11. B plus equals 1. And this will be a while. Incompatible types. That's fine. Fine, and then here as well. It.sphere has no member called create. You're right, it's sphere.init. Then express a material found type. Material with an S. Enough? Yep, it tries to render it. It's gonna be awfully slow. But I think it should be done. Oh, I didn't take a look at what the I didn't take a look at what we should do for these. So it's going to have a bunch of random little spheres everywhere. I'll have to set that up. We'll see how that changed. Well, I mean, it did change. Wow. Okay, so now we have the random spheres. Camera's in a different location. So let's modify the camera settings. 1280. I am not doing a 500 sample render yet. Default is 20. Position look from is 13, 2, 3. The look at is 0, 0, 0. The up is 0, 1, 0. The focus angle turns to 0.6. Focus distance is 10.0. Default is 20. Max at 50. 1200. Aspect ratio. That's set up. Okay. Now let's just add these last remaining objects. So var material 1 equals dielectric material net 1.5, material 2, Umbertian material init vec3 init 0.4, 0.2, 0.1, var material 3, metal material init vec3 init 0.7, 0.6, 0.5, 0.0, var sphere 1, sphere.init 3.init 0, 1, 0, 0, material 1 dot material, material 1 dot material, var sphere 2 is sphere, init vec3 init -4 1 comma 0 0 material 2 dot material, and var sphere 3 is sphere, init vec3 init 410 1.0 material 3 dot material. Go. And then we'll do try world objects append sphere 1 hittable, try world objects append sphere 2 hittable, try world objects append sphere 3 hittable. I think we're good. Be able to run that. It's gonna be pretty slow, I think. It should be pretty slow. But we'll be able to get it. This is at 10 samples. A 500 sample, that's gonna take a while. But I'll probably use that as the final render. But I think this is the last render of the book, and I think we're done. We should end up getting a result that looks somewhat like this. Of course, it's gonna be random. And it's gonna have a little bit of that defocus blur that's gonna look pretty nice. As we're getting lower, I think we're getting more hits, and it should start speeding up as we get less and less hits. Yeah, it's starting to speed up again. We open the test ppm. Yep, there we go. We got our own version of this render. And it looks pretty cool. So the dielectric has that like upside down looking view. Some of these dielectric random ones have that. That's really cool. I really like that. Yeah, this is a really cool result, and this is the end of the tutorial. I'll probably make a repo on GitHub and post all the code in this final form here. And that's been the entire Ray Tracing in 1 Weekend series. Or not the series, but the first book of the Ray Tracing in 1 Weekend. All in Zig, and all done right now. Thanks. Please leave a sub, and I'll see you guys later.